Being shared with community, something shared public. We're good, right? Right?
I don't know that's it. That's it. Last week, the week after today.
We're watching real time here. Extreme detail. I already did actually. Yes. I posted the Hangouts and I posted the YouTube link. Here it is. Yeah, the people lagging, like 30-second lag, because it's working.
So it would be nice if people who stream would post questions. I think you have to set that when you first create the stream.
I think people can post comments on YouTube as well for it. But it's just all on it.
Oh yeah, I'm gonna try it.
I didn't promise that we would be able to.
I'm more worried about the audio.
I was thinking about doing an air cat. No, I don't think it's a bad idea. Like, the more the merrier.
I checked that out. It usually like nothing on there.
Yeah, they give it time, I get filled up. Stand here or you gonna sit?
How they hearing good noise on wondering how they can control it.
You do? Cool.
You tell people to use the comment screen. All right. I can try and watch that.
Hey everyone, we're gonna give just 2 more minutes. I think that's a little bit of a cue. So, last chance, grab anything who are interested in, and I'll just give this pre-announcement. I'll repeat myself. That if you have any noise, wrappers, cans you have to open, things like that, please do it now. During the presentation, it's very disruptive. So, enjoy. We'll get going in just a moment.
No, go ahead.
I'm sitting here.
No, I'm okay. Don't worry about
All right, dramatic music down, and I think we're ready to go. Thanks, everyone. Welcome to a special meeting of the New York Linux Users Group. This is an additional meeting to our normal monthly meetings. Tonight, we are going to be hearing about Systemd by its primary author, Leonard Plugger. More or less? I'm trying. I'll let him say it again later. I'd like to say how much we appreciate today's host, Facebook, for providing us with this space, and thank you to everyone who's here for taking the time out to join us. Tonight, before we get started, we have our usual requests. The first one is silence your cell phones. The second one is no snacks and noisy wrappers or that make noise when you eat them. And if this means like pouring your snack into a cup or just walking away, again, please do that. And the last is we're going to be taking questions at the end. Yes, I know. Take questions at the end. There are 2 microphones here set up on the side, so when the question and answer time comes, we just ask you to file to one side or the other and ask questions. That way everyone will hear your question, conversation, discussion, whatever. Our next regular meeting will feature a talk about the programming language Rust by one of its core members, Steve Kladnick. In case you're not aware, he's mostly in charge of the documentation, but that's a big deal. The talk is titled Why Rust? That will be on Wednesday, July 15th, and that will be at Bloomberg. Again, I'd like to thank today's space sponsor, Facebook. In addition, though, as we always do, I'd like to thank our regular space sponsor, Bloomberg, and to acknowledge our other sponsors, past and present, IBM, Canonical, Brandor Group, Google and O'Reilly Media for their support. In addition, NYUG would not be able to function without our many volunteers who have contributed greatly over the years. If you see anyone who is participating in the group and helps out, please, give them a thanks. After the meeting, Facebook has generously offered to host drinks here for a bit. The drinks have already started flowing. If you don't have one, come grab one. If you see them, there's some tables. But we will be kicked out of here at 9:30, and we will move from here to the White Oak Tavern at 21 Waverly Place, between Waverly and Green Street. No, it's not between Waverly and Green Street, but it's the White Oak Tavern at 21 Waverly Place. So announcements. First one is for workshops. Please talk to Hannah in the back there. She's waving her hand if you're interested. There will be a workshop tomorrow at City College, right?
Yeah.
So talk to Hannah or Rob or anyone else who is a regular attendee, or look at our meetup page for information about that if you're interested. And that will be at City College at 138th Street in Amsterdam. In case you missed it, you can grab a Linux DVD and install media from the butcher block table back there, the one on that side. Those are yours to keep, yours to try, to work on, and haven't had time to download it, haven't had time to put it on Google Media. There you go. It's for you. Please give it a shot. Take them home. Now, as I said, we're going to have questions at the end. And note that at the end of the presentation, there will be a trivia round where, based on what Leonard says, he will ask you questions. You will receive, this is a bit unusual, but we will be offering the normal fare of books and ebook vouchers from O'Reilly, books from not O'Reilly, a different publisher, Addison Wesley. But we also have a bunch of probably working hard drives. They are something prototype drives that have been given to some of the kernel developers to see if they work. And not all of them have been opened. Some of them have. You get to take one home and see what it does to your computer. If that's that's pretty much the size of it, right? All right. So yeah, I don't want to make any promises here about the suitability of these things for any purposes expressed from the file, past, present, whatever. So yeah, so stick around if that interests you. Does anyone else have any announcements about events going on or anything else they'd like to mention that people here would be interested in attending or anything like that? Come on up, grab a mic.
Hello? All right, so in about 2 weeks' time, starting July 13th, NICE Camp 2015 will commence at the United Nations. It'll be a full week of Drupal, web sprints, and classes, all free. Just sign up at nicecamp.org for details, and come down and check it out.
All right. So, does anyone have any other announcements? Anything else they'd like to mention? Okay, if not, then please welcome Leonard Pottering with his talk on System D. Sorry, quick. One note is that when question time comes around, I know that some people have strong feelings one way or the other with regards to System D. I'm going to ask that everyone keep in mind that we are drinking. Please be aware of your behavior and present yourself well to your peers. All right? Thanks.
Good. Hi, so I'm Leonard Pottering, that's the correct pronunciation of the name. I'm going to talk today about System D. I have quite a few slides, and I will talk a lot, I think, but in the end we'll do a Q&A, and I kind of would like to put the emphasis on the Q&A so I can actually answer the questions that you might have, instead of me just talking random stuff that came to my mind when I put together the slides. Yeah, we'll start out with something more superficial, and we'll then go into a little bit more detail as the talk goes ahead. So, yeah, what is System D? What is that again? The way we say, like what we say that it is a system and service manager. So it manages the system and it manages services. Managing the system is a very generic term. It means a lot of different things. It's also like, I mean, traditionally the name init system was used for that, and initially systemd was just an init system, but nowadays it's quite a bit more than that. And the way we say, like, it turned into something that it's not just really the pure init system, but it's more a set of basic building blocks to build an OS from, right? The background from that is basically that the init system is really just the first process that is started on the system. But we realized that as we put together systemd, that it is not done. Like, if you really want to bring up a system, then there are many more components involved in bringing it up. So we added a couple of components bit by bit that manage the system, that manage boot up, and so it's now like a set of a large number of separate tools, like 69 tools or something, or we actually might have more by now. Yeah, so we call it a toolbox. The tools that are involved are, like, you don't have to use them all, right? But it tries to cover a good chunk of what is usually required to bring up the system and keep it up. A bit about the history on systemd. Systemd was started in 2009, so it's kind of like 6 years ago. We started working on it a long time before we actually announced it. Actually, the real story behind it goes like this: that back when I started working for Red Hat, we did a lot of stuff that was on the lower level of system. And I talked to a couple of people, and we always came to the conclusion back then that we needed a better init system, right? And then one day I actually started working on one, and I called it Baby Kit, which I found funny. But I'm not sure if everybody else found that funny. But then some guy from Canonical, Scott Remnant, actually started to write another init system called Upstart, and he actually pushed forward. And so I started working on Baby Kit, and that was it for a while. But and then Upstart took over many of the distributions. But eventually we realized that actually Upstart is not really how we saw that an init system should work like, because it was, in our eyes, a little bit too simple, right? I'll go into a little bit more detail later on why we solved that. So eventually we decided, okay, let's resurrect the efforts that I had begun and turn Baby Kit into something real, and that we call systemd then. So yeah, it's in 2010 we actually made the announcement. Like, I put together a big blog story, and a lot of people hated me for that, but yeah. It took us about a year to actually get it into Fedora and be the default. Like, looking back, that's actually pretty crazy that it took just 1 year from the first announcement. That wasn't even the first release, right? It was really just the first announcement to get it accepted into Fedora, not only as a component, but actually as a default. So we were quite happy with that. Today, it's pretty much standard in all the distributions, like at least the big ones and the commercial ones. There are, like, it's easier to list the distributions that have not adopted it, which is like, it doesn't exist at all in Slackware, and in Gentoo, it's not the default, but it does exist. So yeah, we have pretty good coverage. Like, it was released with RHEL 7, which I guess is the biggest commercial distribution. So yeah, in a way, we are a bit surprised about this as well, but we managed to win over the entire Linux ecosystem this way, with some exceptions. So yeah, that is why you should probably care, because, I mean, sooner or later, if you're using Linux, you will probably encounter system one way or another. So what was actually before systemd? I already mentioned that there was Upstart. But before Upstart, there was even something different, which was system5init. System5init was universally used across all distributions. It is a very simple init system. It originates from System5, hence the name. But Linux used an implementation that was completely separate from that. But it had, I mean, it worked, right? But it was also very simplistic, and did not really have any concepts of dependencies or Actually, but the basic System 5 init system didn't even have a concept of services, right? For starting services, it required that shell would be glued in to actually make it happen, right? When distributions like RHEL actually adopted Upstart, they continued to use it pretty much in the System 5 init compatibility mode, right? They didn't actually make use of the Upstart features. Yeah, but anyway, the next one was Upstart, of course. Upstart was for a long time used by default in Ubuntu, and yeah, that changed a couple of months back, actually. So yeah, on record, I can say that Upstart is actually really good code, right? Except that the reason why we saw that it would not be the way of the future and not be the way how we should solve these things were mostly technical reasons about the basic concepts that it implemented. To explain that a little bit, what I mean by that, it's with Upstart, it was strictly event-based. So if you put together your system, you would say, if this event happens, please start this. And if that event happens, please start this other thing, right? So if you then programmed, or like if the engineer from like the distribution vendor or the admin would put together the boot process of the system, they would basically define things like, okay, there's this event and this event, and then would glue stuff to that. And then putting together the entire boot process would mean defining a lot of events and then glue them all together with doing the right things in between. For us, this always appeared as being the wrong way around, right? Because we thought that an init system should do dependency management, right? So that instead of declaring what happens when, you say, this is required by that, and then you, at boot time, you just say, okay, now boot up to this goal. And then it's up to the system to actually figure out what to do when, what to actually start at which point in time, right? So to break this down in other words, while Upstart effectively maximized what we booted up at the system, systemd tries to minimize it, right? Systemd, you tell systemd basically where you want to go, and systemd calculates the minimal set of services of things that it needs to do, execute exactly those, regardless what it is. Upstart, because you actually, the developer has to sit down and write out these dependencies. It would basically be the job of the developer to calculate what shall be started in which case. And because he could only do that once, right, you would do that in a way usually they would have to maximize it because they wanted to cover all the use cases. I hope that's in some way understandable, the concept there. So yeah, and we saw that's a fundamental issue with how Upstart was designed, and we thought, well, if we would fix that, we would turn Upstart into something completely different, because it would be turned from an event-based into a dependency-based system. And that's the reason why we then said, okay, that really so fundamental change that it does not make sense for us to improve Upstart, even though the code base was excellent, and Scott did a really, really good job. He had unit tests and comments and everything. It's one of the best pieces of code we ever had in Linux, anyway. So yeah, I think the summary is basically Upstart was great, but it was way too simple, and it let the admin and developer solve algorithms where we believe that it should be the computer that solves it for you. So so much about the background. When we started systemd, we, of course, were looking for inspiration. The obvious two inspirations were, well, Upstart and System 5 init, but of course, they weren't the only ones. One of the major inspirations, if you start a project like that, you better sit down and do your homework. So we looked around. The Launchd is the Apple init system, basically, or it's one of the Apple init systems. Apple has many. Launchd was a very different topic, very different concept, right? They didn't have dependencies, and they didn't have events or something like that. All they knew, all that the Launchd knows is services, and it puts a very high focus, very strong focus on socket activation, if you know what that is. Socket activation is basically a concept. It's very old in Unix. Initd, right? Initd is this thing where where the ING super server listens on some ports, and then when a connection comes in, actually starts a service, right? So it's effectively a way how you can offer a lot of services on your system without always having run the actual services and consuming resources, right? So it's a tool to increase the number of services that you can run on a system. And it's also a technique to make things more robust, because it basically means that if something stops, whatever, it will be automatically restarted when the next connection comes in. The main reason LaunchD used this concept was actually, though a different one, it allowed them to get rid of dependencies. The reason for that being basically that in LaunchD, all the services, like all the sockets, are bound in a very early state at boot, and then then basically all the other services would just be activated as soon as something connected to these sockets, right? And then simply, like no dependency had to be declared explicitly, because implicitly, when some piece of code wanted to talk something, it would connect to that socket, LaunchD would automatically start that service, and then you hence there was never a need to explicitly configure like the dependencies and the order in which things have to happen. It's a very strong, very powerful concept, I think. But I also think it's not sufficient to boot up. And the Apple people realized that as well, which basically had the effect that the early boot process on macOS is actually not done with LaunchD. There's basically like the place where it mounts file systems and this file system checks and these things like that is done before LaunchD. Anyway, I don't want to talk too much about LaunchD, and I'll leave it at the superficial thing here. But it's a major influence, right? It's really nice design coming out of Apple. I mean, if you compare the code bases, though, Upstart was a much better piece of code. But yeah. And then there's SMF. SMF is a Solaris service management framework. It's part of Solaris. It's something that Sun came up with. And it was actually excellent for its time. Right, nowadays, if we look at it, it uses a lot of XML and these things that kind of went out of fashion, right? It appears to be something from the 90s. I mean, it is something from the 90s. So, but it has a very strong design. Like it introduced like service descriptions where you could actually write down what should happen in a more declarative way. So it would leave all the iterative languages in the past, how you start services, like system 5-minute scripts, of course, are programs. I'm pretty sure most of you have dealt with that. And then SMS, that everything was declarative. So yeah, for us, it is one of the bigger influences, because they did really good in engineering, and they made sure that they have all these enterprise features so that they can restart things and things like that. So what we did with systemd is basically just re-implement everything that we learned from the 4 other implementations that are the best influences for us. So in a way, systemd is not anything really new. It's just something we copied, where we copied the ideas of other people. But that's how open source works, right? Okay, so much about the influences. Let's focus a little bit on modularity. Systemd is quite modular, though some people will actually disagree with that. Like, they will disagree that systemd is modular. The reason I say it's modular is because I already mentioned that earlier. It's like this thing that has 70-something binaries, and which ones actually get built, you can relatively freely choose it at build time. So you can turn off or on pretty much every component of systemd, except for basically 3. One is systemd, like PAD1 itself. One is the journal, which we'll talk about later a bit, and one is UDEF, device management, right? Because they are really necessary to bring up the system. So those 3 are not optional, but pretty much everything else is. And you can package them. You can decide to not build them. You can decide to not package them. It's completely up to you. Yeah, the reason some people say it's not modular, though, is because every one of those modules kind of requires the system to be around, because it's kind of the basic APIs that we provide. So something else I would like to say is that for us, alternatives matter, right? So as mentioned, the journal is not an optional component, but we completely understand that many people want to run an alternative log implementation, right? Like one of the classic ones, rsyslog, syslog, and things like that. And that's completely fine, right? Like by introducing the journal, we made very clear that this is not like, while it can replace our syslog on syslog NG for many use cases, we also know it will not for many others, right? So when we introduce it, we make sure that you can run them side by side, and then our syslog and syslog NG can get the data. But this pretty much for all the components of systemd, this was important to us. Like, for example, we introduced a way how you can start services based on time, right? And that is very similar, of course, to classic Unix cron. But we really made sure that you can run them side by side, and most of the distributions still do, right? Like, so even though systemd covers these areas, it doesn't mean that the downstairs distributions strictly have to follow that. I mean, we encourage everybody because we think that systemd is great and you should just use it. But of course, that's not our decision. It is a decision of the downstream distributions and of the users, of course, what they actually want to run together. But just to make that clear, alternatives matter, right? This doesn't mean like, again, you cannot disable the journal or something in systemd because we actually need it. Like we need it because basically every service that we start gets this std out and stdr, like where it basically writes logs if it's not writing on syslog directly. It writes like we want to collect that and write it and then and store it in a central location where logs are kept. And to be able to do that, we're actually connecting all these things to the journal, like via a very simple protocol. And things like that, because for us logging is like this core component of service management, you cannot actually just rip it out because then suddenly stdr and stdr, nothing would be linked out anymore. And it's also about, right, for systemd, it was really important that we actually collect logs for the entire runtime of the system, right? Which is a major difference to classic System 5 init, because in classic System 5 init, up to the point where syslog was started, there was basically any logging happening, right? Because syslog was a service like any other, and that meant it would only be started when we enter run level 3 or something like that. But if anything tried to connect to devlog, like the logging socket, before that, we couldn't do that, right? Like there was nothing there, and it would go nowhere. So like people came up with solutions for that by like Debian, for example, shipped this tool bootlogd, which tried to scrape from what was actually output to screen back and write that to a log file. It's just weird. I don't know. It's the wrong way to solve these things. For us, it was really important that all the logs should always be collected, right? And that meant from every channel that we get them, and at any time of the boot process, meaning in the init.id as well, because yeah, for us, I mean, the init.id is like the earliest boot phase of the system. And if something fails, it's very likely to be that, right? Like, so we shouldn't throw those logs away. It should be at the core of what we collect. Anyway, coming back to this thing, right? Like, we'll talk about the journal a little bit more later. But yeah, for us, alternatives actually do matter, even if people say like claim otherwise. And we will make sure to make them work the best way. Like for the journal case, actually, even if you decide to run R syslog G, you will actually take benefit of the journal thing because it will actually collect so much more data that will end up as well in our syslog than before, right? Like, so we actually, like, if you run it together, then you get all the init.id logs in your R syslog history, which is of course great. Anyway, so it is essential to us. So, so much about like the general ideas behind it. Let's actually start looking at the concept that it introduces. Consistently, like, I mean, this is like basic, right? If you ever played around with systemd yourself, you probably know most of that. But for those who have not, this is basically where you can get a basic introduction to the concept. So in systemd, everything's a unit. Like a unit is just a generic term we use to describe basically the nodes and the dependency tree that we built. These units are named somewhat dot and then a type name. And there are, I think, in total about 9 unit types now. These are some of them, like .service, .device, .target, .socket, .mount, .timer, .automount, and a couple of others. Between these units, you have dependencies. So there are requirements and ordering dependencies, and those are actually orthogonal, right? Like, so it's not how it Like if you have a System 5 service, right, like with the LSB header, like all of you probably have seen in one way or another, then you have these things like it says that it needs to be started after or something like that. And that usually means that, yeah, the other thing should be started first, and secondly, I want to be started after that, right? Like, so that's both two things. It pulls in something and it orders something. And systemd, that's completely orthogonal, right? So that basically means that if you order something and say, I want to be started after something, that doesn't mean that the other thing is automatically pulled in. And if you say, yeah, well, I'm a unit and I want something else also to be started, that does not imply that you are started after the other one. But if you have to define both orders, then you're good. So, to give an example what that all means, right, like with the dependencies with the units. So here's like, I mean, this is not a tree right now, we have to keep it simple, but it is actually a complete tree of dependencies. And the reason I'm not putting up a real tree here is simply because it actually can grow pretty large to put on the screen. Like you can actually, like systemd actually has a tool that can show you in a GNU plot, no, not in a Graphviz, sorry, in a Graphviz generated form, basically the entire graph of dependencies that the system knows about, like every service that depends on every other service in a gigantic dependency network. But it's actually probably not useful to put on the screen here because nobody will understand anything because it's so gigantic. Anyway, so I isolated one branch of this tree out to just give you an idea what we actually need with these units. So there's actually data in there here. I don't think so. Okay, I mentioned earlier that the way systemd works, right? Like I said, we focus on where we want to go to, right? Like the target, and then we come up with the dependencies that we need for that. So in this case, our goal is to boot into multi-user target. To explain what that means, target is basically very much what maps to a run level in System 5, right? So it's basically a description of a number of services, number of dependencies, right? Like just a quick way to group services that need to be started so that you can reference it in one go. Classically, System 5 knew 7 run levels. And of those run levels, like there were 3 that were pretty much irrelevant because they're about shut down with the startup. And then there was basically run level 1, 2, 3, 4, and 5 that was really interesting. And most distributions mapped some of them at least in the same way. But so the really important ones are basically just 2. One of them was called multi-user, in most of the distributions. The other one was called graphical in most of them. But I mean, that's just an implicit name. Like you would never tell System 5 init about that name because System 5 init didn't even know the concept of names. It only knew the concept of these 6 numeric run levels. So multi-user target is basically what maps to run level 3 on most distributions, at least the Red Hat-based ones, which is basically the normal state that the system is in, unless it like a server is in, basically. So in this example, multi-user target has a dependency. In this case, the arrow shall imply both an ordering dependency, like meaning that multi-user target should be started after httpd.service, and also should pull it in, right? Like so, also both ordering and requirement. So in this case, multi-user target requires httpd.service, requires basic.target, requires localfs.target, requires home.mount, requires this weird thing, and requires that weird thing. To explain what that means, targets are basically run levels. httpd.service is, you probably guessed it, Apache, right? Like the service that wraps up Apache. Apache pulls in basic.target. Basic.target is basically the basic system setup. It's another run level. So to explain that, in systemd, the targets are different from classic run levels in the way that while run levels, you only had one active at a time. In systemd targets, you can have as many as you want active at the same time, right? Another difference, of course, is that they're more expressive because you can actually give them names. So to say this with another word, basic.target is basically a generic way how you can say, yeah, the basic system, right? Everything that I need to run normal service, to like a normal system service like Apache. Basic.target, multi-user.targets are all targets defined by systemd out of the box. But you're welcome to define other ones, named the way, whatever you want to name them. but usually we'll come back to multi-user.target and basic.target because if you take third-party software, it will probably plug into these two because, well, that assumes that they're used. Right? Basic.target is, again, this generic thing for wrapping up the entire base system. Local fs.target, which it pulls in, is basically a target that groups all the mounts that are required, right? Like if you have your system set up so that you have a mount on /home and a mount on /var and a mount on /srv, then all of these are together mounted on local fs.target. In this case, I only looked at one of them, which is home.mount. So home.mount is basically a unit that encapsulates a mount point, right? Like something, like if it's there, then it's yeah. And to activate home.mount, we actually first need to make sure that the file system underneath it is file system checked. So for that, we have the systemd-fs check service. This is actually, this uses an advanced functionality of systemd, which is instantiation. Basically allows you to define a service once and then instantiate multiple times with a parameter, right? In this case, systemd-fs check is something that is shipped by systemd. It's basically just an invocation of the fs check tool on the device that you see here, right? In this case, /dev/sda6. And then that thing, of course, needs to wait until the device backing it has shown up, right? Like it makes no sense to start that before the device has shown up. So yeah, basically what you see here is basically one change through the entire dependency tree. This requires like this, the things on the left side basically require this stuff all the way, always on the right side. So the device has first to show up, then we file system check it, then we mount it, then this way we group all the other mounts so that for everything else it happens the same way. Then we start a couple of other things to bring up the service, then you restart HTTPD, and finally we reach multi-user.target. So I hope this kind of gave a bit of an idea how this works. So like these units can always be started or stopped, right? Or something in between. So basically, dev SDA device is initially not started, right? But at the moment where the device actually appears and is registered in the system, the kernel learns about it, it becomes started. Well, systemd-fs check, of course, not running initially either. But at the moment where systemd actually forked it off and made it run and the process is around, you can see it in PS. That's when it started. Similar home.mount, in this case, it means that it's mounted. What starting means, and yeah. So yeah, I hope this kind of gave you an idea what this is all about. Again, this is just one branch, one pass through this dependency tree. If you want to look at the full one, then there's a tool called systemd-analyze plot on your system. And if you invoke that, you get this gigantic graph, that you can then that basically generates an SVG, and that SVG you can look at, and then you'll probably be overwhelmed because it's so large. What you can see about this is general goal is wait exactly for what we need. And we start and wait for as little as necessary, and we do it as parallel as possible. How parallel that is of course that you won't see that from the path that I've shown here. But I mean, just in your head, just think about that local fs.target actually not only pulls in home.mount, but also var mount and whatever else you want to have mounted during the early boot phase. I hope you can actually read that. The font might be a bit too small. To give an idea how a service definition actually in systemd looks like, I put one here for a completely random daemon that I had on my system, which is a NUMA daemon that manages application locality with something was, well, servers. I introduced you to all the concept of a unit, right? Most of the unit types actually have a file on disk that is exactly named the same way as the unit is named, where it gets its configuration from, right? So in this case, you can use the command system control cat numid to actually look at the service definition. This file here, user.lib system numid.service, looks like this. It contains the information how to start numid and some dependency information. In this case, there's none because it's a very simple service and we didn't need any. It also contains information about documentation, about how, when the service is started, it will actually notify completion and things like that. This is an ini file, like a Windows ini file. It's declarative, as you should notice, right? Like, I mean, in your head, just think about how a system5 script looks like, right? I didn't put any in my slides because, that could usually get too large. Like, I mean, they're awful system5 scripts in this world. But what you should get from this here is that it's declarative, and usually it's actually very short, right? Like, for example, in this case, we declare how the service gets started, but we don't actually declare how the service gets stopped. Systemd will actually take care of that automatically for you, right? Because most of the system services that there are actually can be stopped the same way by sending them a signature, and hence that's what systemd does by default. So you can explicitly configure what it does to shut it down, but usually there's no reason to, because systemd implements it generically for all daemons, and daemons that don't work that way probably should be fixed to actually work that way, because it's how Unix works. But anyway, so that makes it much more simpler. To give an explanation about what this all means, so the first section is unit. In the unit section, basically, you find settings that are generic, that apply basically to all unit types, right? If it's a service, if it's a target, if it's a mount, if it's a whatever it is, that's a generic part that applies to all of them, right? Like that, or that has like the fields that exist on all unit types. In this case, that's a short description string to help the administrator, and there's a documentation string which takes a URL to help the administrator in case he wants to know more about the thing. In this case, it's just a link to a man page. And then the second section, which is service, in this case, is actually specific to the service type. In this case, it's a service, so it will actually contain information about starting something. Exec_start is, well, I mean, I figure you guessed that is just the command line that's actually started. Type equals forking is basically a way how you tell systemd how the daemon reacts, how it tells systemd when it's finished starting up. So the logic behind that is basically, well, if you start 10 services and they require each other, think of MySQL usually has to be started first, Apache second, because Apache often connects to MySQL. So it should be MySQL that started first and Apache that started second. So you have to have a way how systemd knows at which point in time actually MySQL finished starting up, right? So that at that point in time it can actually go and start Apache. The way how this works in classic Unix is by double forking, right? Like on classic Unix, if you start something from a system5 script, the way it works is like let's say you start MySQL, or let's take Apache. So you basically have this invocation of the Apache binary in system5 script, and it basically says daemonize, and then what happens in the background is that the shells forks one process, which we'll call the parent process, which will then fork twice. Like it will generate one child first, another child, and then grandchild of what we call the parent. Is actually the main process of the daemon and stays around. And then the lower one initializes, and after it initializes, it tells the parent again, and that's when the parent then exits, right? This is relatively complex logic. It has been in Unix that way since forever. The double forking is something weird that Unix requires to make sure that the parent is owned by, like the parent process of the actual daemon of TLD1. I don't really want to go into details about why that is that way and why that's weird, but long story short, if you have a daemon that works like that, which many daemons are because that's Unix, then you have to put type equals forking. It basically tells systemd this is a daemon that double forks, and when the parent process exits, it's the indication that the child daemon, like the child process, actually finished initialization. You can start calling. Yeah, and then the last section is about it carries information that when that service is installed on a system, what should actually happen? Like where should it be hooked into the rest of the system? In this case, it's basically it says, yeah, make sure that if the service is installed, if the RPM is installed and the service is enabled, make sure that it's started by multi-user target, right? Again, multi-user target is this thing that is basically run level 3. From system. So it basically says, yeah, start this at run level 3. And that's already a very simple service, and I think it makes a lot of sense. Like you can probably understand much of this. Not all service files will be that simple, but many actually will. So much about service files. So let's talk a bit how you can actually interact with the system, right? How you can actually start a service, stop a service, and things like that. So the first line is system control. Like a system control is basically the main program you need to know if you want to interact with systemd. It is like if you want to compare that with classic system 5 init, then it incorporates both the service command, like I mean at least the Fedora people will know, or Red Hat users will know the service commands. Like Debian, I think most people probably start with the init scripts directly without that tool. But anyway, the service command is basically how you start it and stop the service in system 5 init. But it also incorporates the stuff that actually enables and disables services, which maps on Red Hat to the check config command, and maps on Debian to the update rc.d command. Right? So the first two lines basically give you an example how to start a service. In this case, like the first line is the correct one, the official one, how you should be doing it, at least if you write scripts. So basically you just say system control start, and then the full unit name. And numa d.service is the full unit name, so we type that, will work. Perfect. But of course, everybody's lazy and doesn't want to write that suffix there all the time. And in 99% of the cases, you probably care only about services. So you can actually leave that off. And systemd will automatically imply it's a .service if you don't specify otherwise. So yeah, the correct way is that you write the full unit name. But if you don't, we try to be nice to you and fix it up for you. So that's how you start a service. That's pretty easy. Then, of course, the other command system control stop, you stop a service. System control restart, you restart a service. System control status will show you the information about a service. If I would do the demo, like the thing on my laptop, I would now show you how that actually looks like, so that you can get an idea how it feels. System control status is actually much more interesting than what service, like the old system 5 init command service status would actually show you. Because it not only shows you whether it's running or not, but it will actually give you an entire process tree of all processes that the service started, right? For example, if you have Apache, right? Apache has one main process, then it forks off a couple of worker processes that actually process the HTTP request. And those then fork off a couple of CGI scripts, right? So system control status will show you the entire tree, right? It will show you every single service that belongs to every single process that belongs to a service. System control status will show you a lot more information actually. It will show you information like at what time and how long ago was the service started. It will show you things like, it will actually show you the last 10 log lines by default of the service, which actually I personally think is absolutely the most important feature maybe of systemd at all. Because I mean, if you manage services, right, and you want to know, is that service healthy? How will you figure out, like, what would you do to figure that out, right? You look at the logs, right? So if we talk about service management, then logs are very much at the core of it. And that's, like, I mean, it's basically the reason we created the journal. We wanted the ability to, if you type system control status, to show you the last 10 log lines that were generated. And that sounds like a very easy problem, but with classic syslog, that was not possible because classic syslog doesn't carry enough information. Like it does not know which service actually generated a message. The service can find anything. It can, like MySQL can pretend to be Apache on classic syslog, and we have no way to filter that out in the end, right? So that's the reason why we created the journal. We just wanted to make sure that if you type system control status, you see those 10 log lines, because I mean, it should be a comprehensive tool that helps you to figure out what's done. It will also show you a lot of more information. Like it will show you if you enable it, or if it's a vendor default, it will show you something like if you make changes to the configuration file, like for example, because you said, okay, that's a service, and I want to bind it to CPU 2, 3, and 4, and you did that, then system control status will show you that you made this modification of the default thing that the vendor did. It's a really, really useful command. It's supposed to be human-friendly, right? Like it should show you in a very condensed way a lot of useful information that we think are probably most relevant if you're an administrator and want to know what's on with the service. Then there's system control show. It basically shows very similar information, but it's supposed to be the more machine-readable way to get to it. right? So system control show basically shows you a list of I think like 300 properties now for service. And then basically, if you write a script, you should use show, not status. Because status, we take the liberty to rearrange things a little bit to make it friendly for you for humans. System control show is the thing that we think is we focus on making it readable by programs and the one that we keep stable. Then the system control cat that basically gives you outputs you basically the configuration file, like the unit file that I showed earlier. Like here you see that, right? Like the command line that I use system control cat numd, and then I got this. It's a really useful little command. And then system control edit. I mean, system control edit and cat, you can use them, you don't have to use them. The unit files are just on disk, right? You can look at them in user lib, and you can see them, or if you can actually overwrite them and put that in etc. But system control cat is a really nice way how to not have to go to disk in the directory and look through it. It will just do that for you and just dump it. System control edit is a way how you can make changes to unit files, because like usually the vendor defaults are not what you want to run, right? Usually, like often they are, but sometimes you want to do things like make a change here and there. Like you want to tell MySQL that it should use a different CPU, different nice level, different whatever, and you should be able to do so. So system control edit makes that easy for you. And then there's system control enable and disable. System control enable and disable is basically what check config and update RCD did before. It basically hooks in a service or hooks it out of the system, right? Basically, it just interprets the data that's shown here and makes sure that, yeah, multi-user target pulls in this case, this stuff. So basically, a service by default that is not automatically started at boot, it's not automatically started by any other trigger until you type system control enable, and then it's pulled in by default. And if you want to disable it again, use that. That's kind of like, yeah, if you know check config update or c.d, you should know about the concepts. Okay, so much about the really basic concept of the way how you interact with things. Now I'd like to focus. What time is it actually? Let me check that. So let's talk about the other components that System actually includes. It actually, as mentioned, includes a lot of them. So my slide actually shows a lot of them. But let's get started with a little bit of an overview on some specific ones. System UFD used to be an individual project. Like a couple of years ago, we merged it into systemd because we could share no code and it was written by the same guys anyway, and because it's actually a very essential part of the system to bring it up, right? Like, and we felt that yeah, it should be just a part of systemd. Its purpose is basically it gets notifications from the kernel when new devices appear, and then it will probe capabilities, load kernel modules, and these kind of things, and announce the device availability to other applications. Right? That's one component. It's like even on if you use System 5 init-based systems or upstart-based systems, you will actually already find UFD because it has been part of Linux since a long time. Systemd login is a component that's primarily useful in client systems, and basically tracks user sessions. Right? Like it has an API how you can query. Okay, which users are currently logged in? Which sessions do they have? It is a little bit like console kit. If you ever played a more idea version of it. It is pretty advanced. Like it has things like concepts like seats, so which allows it to be completely multi-seat aware, so that you can actually have one system that connects to multiple displays down to the keyboards. And the keyboards and mice and screens are connected, like bound together, so that you can distinguish the seats. Yeah, and then there's systemd journaling. I already talked a bit about the journal. It's our logging system. It's very powerful, I think, and it fixes a lot of issues that we saw that journaling, that logging had before. I already mentioned a few. There are a couple of others, like something that I, for example, think is really important about logging is fakeability. What I mentioned that earlier, that on syslog, basically any process could claim to be any other process, and syslog wouldn't care. It would just store that away, and that's it. Right. So if you as an administrator wanted to figure out what actually wrote that log message, you would just see the logs and couldn't claim anything. So if somebody breaks into your system, the logs would be inherently useless because, yeah, if you broke into the system, you could replace any binary you wanted. You could claim that your MySQL was actually your Apache, or your Apache was actually whatever else it wanted to be. So the way the journal works there is that it's generally structured, right? So it's not just one string anymore, a log message, but it's actually one human readable string plus a couple of additional properties that belong to that message. And we add, like, it feels a little bit like an environment block, you know, right? Like if you type set or something on the shell, like this huge amount of things that you see, because we use this uppercase syntax and equals and things like that. So, and a lot of these fields that the structured log messages have are actually generated implicitly by the journal, right? So it's not the sender, like the actual process that logs anymore, that attaches it to the message, but it's actually the receiver, the journal, right before it writes it to disk, that gathers it in a secure way, right? It asks the kernel for these bits and writes that to disk, so that it cannot be faked, right? And I personally think it's one of the really, really important things about logging, because suddenly you can actually start trusting your logs. Structured fields can also be added by the applications themselves, right? And then, like, we provide a library for that makes that easy. And it's a really powerful tool, like, for example, because the way, like, the call that we provide to actually log will implicitly add things like the code line and the source file and things like that to all the messages, so that if you actually look at the logs, you can click on them and it will actually point you directly to the source where it was actually generated. Anyway, the journal is probably enough material for a completely separate talk, about 4 hours. So I'll leave it at that. Another component that we talked about recently is System Network-D. That we introduced very recently, System Network-D. It's basically, well, as the name suggests, it configures a network. It's basically what we thought that network manager should always have been. So it's a network management thing. It's like the concepts that it introduces, I think, are a ton more powerful than network manager, because the way it works is basically that instead of there being an interface and then you configure it, it's actually that you have these files like .network and .link files, which start with a match section, and the match section expresses basically to which interfaces does this configuration file belong, right? And it could be, it can be very generic matches, like saying this network configuration file belongs to everything that's Ethernet, but it can also be very specific, where you can say basically this network file matches everything that is an Ethernet and has this MAC address, or everything that is Ethernet and has this PCI USB port identification, right? And this is super powerful stuff, because you can suddenly express in a generic way configuration once for a lot of connections. So like Intel is actually using Network-D now to build routers, where because Network-D also has these things like uplink, downlink management and stuff. So that they have basically one configuration for the uplink and one for the downlink, and that applies to all the ports automatically. Network-D is also fully hot pluggable. So if you, for example, have your router there and it already has 10 uplinks and 10 downlinks or something like that, and then you plug your USB Ethernet in there, then Network-D will take notice and automatically add it to whatever you have. It supports bridges, blah, like VXLAN, all the stuff that the kernel supports. What it does not do is Wi-Fi. So like Network-D is, like, we wrote it to be able to use it in an RE, like in a very limited early boot environment, so that we can use it to boot systems from. So the focus for us right now is mostly to run inside of containers on servers and in embedded devices. What is not really the focus for us right now is to run it on desktops, right? Because for desktops you need Wi-Fi. For servers, containers, and embedded Wi-Fi is not that essential. Anyway, the distributions, like I think Ubuntu has decided to switch over at least its cloud edition to that. But we're still in the progress of actually getting into distributions. Yeah, RHEL will probably not make it the default anytime soon. Another component we recently added is system to resolve-D. It's basically something like a DNS cache. The reason why we saw that makes a lot of sense is simply because On the other hand, the way DNS resolution works right now is that every single process uses the same calls in libc to be like to implement an DNS state in every single process, right? Which I think is like from a security perspective is already a bad idea, because every single process will put together DNS packets, will get replies back, will parse that, and yeah, it's open to the network even if it just wants to resolve the DNS name. So the way we thought this should really work is that you like also there's some caching, right? Like because every single process has its own stack, we will not know anything about any other process on the local system already having resolved something. So also we saw like one of the major issues we always saw with we had with DNS is that at least on like my desktop, right, like with my corporate desktop where I connect to the Red Hat VPN, that's usually the zoning problem, like because if I use the DNS server from Red Hat, I will see all the internal Red Hat servers. But if I'm at home, at least, I also have this other DNS server that tells me everything about my local devices, like in my homeland. And then you have the problem, like, what do you do with this? And classically, this was never solved, and you either get one set or the other set, but you will never get both. So the way we thought this should always work is that if we have no information about where to route queries explicitly, like based on domains or something, then we would actually query all this DNS like per interface that we know. So if you are like in a setup like I have with Red Hat and my local network, then we would actually, like if you resolve for the name, try to resolve the name foobar, you don't know where that might be, you actually ask at the very same time the Red Hat VPN DNS server and the local one, and then the first one who gives the positive answer wins, or the last one gives a negative answer, like who says the service doesn't exist. So it basically transparently merges the zones. Yeah, systemd resolving, like we're working on a couple of other things. Right now, we working to add DNSSEC support, because I mean we think that should be just part of systems, right? Like it shouldn't be optional; it should just be there. It should always work. And something else that implements is actually LMNR, which is like it's a Microsoft-defined protocol. It's short for Link Local Multicast Name Resolution. It's a protocol that they came up with. I mean, if you know Avahi, like Avahi is a project that I've read earlier, Avahi implements basically the same thing, but on a protocol that Apple came up with. And LMNR is the Microsoft version. LMNR is implemented by all the Windows versions. And basically what it does is name resolution without a central DNS server within local LANs. So the idea, the reason why they put together is that they, like, yeah, you connect your phone to your laptop and they should be able to communicate by names instead of just IP addresses, right? But because you connect it directly, there's no DNS server or anything involved. And so they came up with this LMNR protocol. We added that to Resolved because we thought it's, well, of course, in the same use case it's necessary. It's useful as Microsoft's use case was. But we also thought it might actually be more interesting thing to do if you have container-based setups, right? Because it allows you to take a couple of containers on different hosts, you set up a VXLAN, and then DNS just works, right? Because it's a multicast domain, like it's a broadcast domain, a single one that you have there, and they will just find each other. And you don't have to configure anything because everything that is in that virtual circuit just knows its own name, and you don't need to set up anything. So it's about making things more automatic. Yeah, we have other plans for that too. So much about resolved. Something else, we added a systemd time syncd. Systemd time syncd is, as the name suggests, it actually synchronizes the clock. It is, well, it's an NTP client, but it's not actually NTP, it's SNTP, which is a simple NTP implementation. The reason we added that is because we thought, well, there's basically no system currently that is connected to a network that should not have the correct time, right? It should be a basic feature of the operating system to have the correct time. And we also saw that it is kind of crazy that what people currently do to get the correct time is install a full NTP server that can listen on ports and respond to clients, right? So we wanted time syncd as something, because pretty much every machine will need it, as something that will just be an NTP client, right? So it's not an NTP server where you just turned off the server component. It's it's minimal. It will just set the clock, and that's it. It's also a lot smarter than the classic NTP implementations in many ways. It's also dumber in other ways, but it's smarter in the regard that it will sleep all the time until it actually needs to do something. Like classic NTP, for example, would woke up every, I don't know, 30 seconds or something to do something. And it's like for embedded devices and mobile devices, it's really not what you want to do. So TimesMT tries to be smarter there. And it also has these things that it tries to guarantee that the clock stays monotonic. So it will, like, which is especially useful for embedded devices, store the last time it ever heard of to disk. And then when the system comes up and doesn't have an RTC or has incorrect RTC or the battery is empty, like on Raspberry Pi, that's basically every boot, it will actually put the clock to at least that time that it stored last time on disk. And that's actually a really, really useful thing because many tools on Unix, like Make, for example, rely on the fact that they want to be able to compare timestamps of files, right? But if the clock always jumps back and forth, you cannot compare timestamps anymore because like sometimes they like even if something happened after something else, the timestamps might still be reversed, right? So yeah, it's a nice feature, right? Yeah, timestamp is a great thing. I'm pretty sure that most clients should, even most servers, should actually run that instead of the fully fledged NTP or Crony thing, right? Basically, my personal opinion at least is that NTP and Crony is something you want to run on an NTP server and not on a normal server, right? Like if I just want to share some files via HTTP, there's no point in installing a full NTP server. But then again, many people disagree with that. It's just my opinion. Electricity machine D, which I will probably talk about a little bit later, it has something to do with container management. That's import D, same thing. There's time-based D, locale D, and hostname D. These kind of belong together. They are not services that run continuously. They're just a way how you can change system configuration. Like time-based D, well, this is basically an API how you can like it's used by GNOME, all the three services to make changes to the system. So it does policy kit and these kind of things. I don't really want to go too much in detail with that. They're very simple demos that only start if somebody requests them and then exit after the one using them is done with it. But it's not just daemons that systemd has. It's also a couple of other services that are short running and are only used during boot. There are systemd temp files. It's basically it's a very useful little tool that is like you're given a configuration file that lists at boot, please create this directory and give it this mode and owned by this guy. And then you can say, okay, and also empty that file and clean up /temp and do a couple of other things. So basically, it's a way how you can remove files at boot. It's a way how you can also declare aging. File aging is basically time-based cleanup of /temp and /vartemp, right? And these kind of things. It runs during early boot usually to set up things before the rest of the system starts up. It's now really, really powerful. You can actually use it to set ACL, set extended attributes, set like the Linux file attributes, like the weird ones that they have, like the immutable bits and things like that. It's a really, really useful tool. And the idea is basically that packages, if they need something special in the file system, just drop in one of these configuration files. But it's also open to administrators. There are systemd sysusers. This is particularly useful if you have something like a system that is stateless, right? Where nothing survives a reboot, which is like containers are usually like that because the containers, like you instantiate them, a lot of them on different servers, but actually the data, like they usually don't store the data locally, right? Like they store it in a MySQL database somewhere else, or they store it in a cluster file system or whatever. But they usually don't come as a home directory when they make changes to it. So systemd sysusers is basically a way how we can implement stateless systems. I don't want to get too much detail about that, but basically the idea there is that you can boot up a system with just /user being around, right? So that you basically take /user, the entire tree, and you mount it into an empty directory, like bind mount, for example. And then the system will be completely fine with that. It doesn't need etc, but it will create etc as necessary, and will create var as necessary. And after booted up, you have the full system, right? And sysusers is now explicitly for creating the system users that are necessary to boot up the system, because the system users, of course, are defined as etc pass WD, right? So if you boot up with a system that has no etc, it will not have etc pass WD, and hence it doesn't know anything about system users, and hence because Apache, for example, wants to run as HTTPD user, you need something that creates a user on that first boot. And that's the system users tool. It's not only useful actually in this case, it's also useful for RPMs and things like that, because it's you know, right now if you define RPM, like in RPMs, if you want to create a system user to run daemon as, then you would do that by actually invoking in the post instance the add user command, or user add, one of the two, depending on the distro. And this is more declarative way, right? You can say, yeah, this is all the users I need, just create them whenever you think it's right, but you don't have to explicitly say that you want to create them, you just say, this is what I need. There's another tool called system modules load, which just statically loads a couple of kernel modules. Basically implements etc modules load.d, where you can drop in files to load stuff. There's system bin format, which is for configuring binary formats. It's like, you know, you probably know that, like how Mono or Java binaries can be made executable on Linux, and so that you can just add the +X bit, and then they are executable as if they were ELF binaries. And that tool manages that. There's system backlight, which is only really useful on laptop, which saves and restores the brightness of the screen across reboots. There's system random seed, which is responsible for saving the random seed to disk and restoring it at the next boot. You want that, especially in service, because if the kernel is freshly booted up, it will have very little entropy. At least in classic system, modern CPUs have entropy generators, so it's not that much of a problem anymore. But it's still useful because you actually are not sure if you want to try Intel and the NSA, whatever is behind that. This is a really useful tool. We'll basically add shutdown, store away the random seed, reboot, will move it into the pool again to make sure that you take benefit of the entropy you gathered on the last boot for the next boot. There's systemd RF kill, which is kind of like systemd backlight, and it saves and restores the RF kill state. RF kill is like the RF, like a radio, the wireless LAN keys if you're airplane mode or not, basically. There's systemd syscontrol, which is a little tool that will apply etc syscontrol D, if you know that, like these little configuration options for the kernel. At boot, there's systemd console, which will actually load the kernel, like the console fonts. Yeah, so much about other servers. Actually, quite like, I mean, this is not no way complete, right? Like, I don't want to drown you with the huge amount of smaller servers that we have, but these are quite a few of them. Let's focus a little bit about the tools how you interface with the system. You already got to learn system control, like we got to know it a little bit. But there are more. There's journal controls, basically how you interface with the journal logs. If you just type it like that, it will actually give you pretty much the output of cut var log messages, right? It will just dump the messages that happened on the system onto your T2Y. However, it's a lot nicer actually than cut var log messages because it will paginate by default. It will actually apply colors, right? Like, so that because the journal, as mentioned, has a structured information. So one of the bits of information that it stores away at disk is actually the log level of each message, right? And then at a display time, it uses that log level to highlight lines for you, right? So it will show normal log lines basically in whatever you configure the terminal to be. But in bright, it will color everything that is notice or higher, like log level notice or higher, and in red, everything that is error and higher, right? You know, like syslog defines these 8 levels or something. Most of them are bullshit on the levels because they all sound the same. But basically, we figured out, okay, let's do some basic coloring, but not too much. And it's basically log notice and up is bright, and log error, log error and up is red. So that's actually really, really useful. Like if you use the tool, you can suddenly immediately see where the issues are, because most of the log messages that are generated on the system are completely uninteresting, right? Like it's just something like information about I started or something. But if something says log something and log error, you should see it, right? But you still want to see the context around. So journal control is a really useful tool. It also does nice things like it will automatically time zone correct the thing for you because the journal actually stores everything. Like it's a huge problem with syslog, I think, because syslog store like the timestamp on the syslog message is actually generated by the sender of the message, right? And that often generates serious problems because it really depends on the configuration of the individual system. And even on the individual root, if you use that, what time zone those messages will be at, and that can get utterly confusing. Like if you, for example, run postfix or something in a chroot, and that chroot thing has a different idea of the time zone than the host does, and you get one stream and it will not carry any the time zone information, you're completely confused what's actually going on. The journal will always store everything in UTC and will convert it at display time, so you can actually make sense of the time zones. And then there are a couple of other things. I mean, again, the journal is something I could do another talk about for 5 hours. So let's focus on login control. Login control is basically the client side, like the client tool to interface with login. So it will show you information about who logged in, what seats are there, what the sessions are. It's actually a really nice tool because it will, like system control status shows you all the processes of a service. The login control would actually show you a similar tree of the individual sessions that you have. And it will also show you like all the user logs and stuff. It's a really nice tool to work. There's machine control, which will keep track of containers. It's kind of the counterpart to machine that I was just quickly mentioning there. There's network control, which is the client tool for network D. There's hostname control, which is the client tool for hostname D. Like basically, it's a tool you can set the hostname with. Not very complex. Time ID to set manual time settings with. Locale control to set locale settings with. Codon control is actually one of my favorite tools. The system D has a component that will actually collect cordams from the system. And cordon control is a tool how you can then look at them. And cordon control, basically if you just type cordon control, it will give you a list of the last cordons that happen on the system. And if you type cordon control GB, then it will actually start GB, like the GNU debugger, and load the most recent cordon and give you the backtrace immediately. And then you can use cordon control GDB and some PID to get to specific other entries. It's an amazingly useful tool, actually. And the cordon collection actually makes sure that cordons are just basically passive logging, right? We think it's a loggable event like any other, and so we integrate that nicely with the logs. What cordon control basically just does is it gets data from the journal, looks up some things from disk and from other places, and then gives you information about a cordon and gives a stack trace about a cordon, and it allows you to start GB. Oh, and by the way, every cordon, if you use this functionality, every cordon that happens on the system will actually get automatically generated and attached as a log message to the system. This is incredibly useful if you can read cordons at least. There's bus control, which is something to do with dbus. It's basically a way how, like dbus is this IPC system that has been around for a long time and which is used by systemd for all its client communications. dbus is a very powerful thing. It's probably also something I could talk about 3 hours for. But bus control is basically a way how you can interface with it, how you can see what IPC services are there on the system, what objects do they offer, what interfaces, methods, signals, properties do the objects offer. You can get a stream of the messages, of the debug messages that actually happen on the system as they happen. So it's a little bit, you can even generate from the DDoS messages a PCAP file that you can then use Wireshark on to actually see what dbus traffic is actually doing on the system. It's like, I mean, to use the tool, you need very limited, you need some, but very limited knowledge of dbus. It's actually wonderful to use it with because it actually has shell completion for everything. So you can just type bus control and press tap tap, and then we'll show you, okay, we'll automatically shell completion give you the service names that are there. You can press tap tap, and it will give you the list of all the objects that it has, and tap tap, and we'll give you the interfaces and the methods and things like that. So it's wonderful to work with. Yeah, so much about the individual tools. Now let's see how much time I actually have. I think like about 15 minutes or so. Well, one thing I wanted to talk about specifically is systemd NSPA, which is a relatively, actually it has been added a long time ago to systemd. So NSPA is a very basic container manager, right? It's something like, so when we were working on systemd, we wrote an init system, right? Like, and if you test an init system, you need to boot all the time because you write something and you want to bring it, you want to see if it works, so you have to boot up your system. And then of course it gets really annoying, like especially if your BIOS is slow and you end up like constantly rebooting a physical machine, you have to restart your Emacs, you go crazy. So then of course we switched to something like KVM to make this a little bit more efficient. But it was still like, because KVM still takes much longer than necessary to actually start up, we came up with this thing called systemd nspawn. Systemd nspawn, in many ways, you could claim it's just a re-implementation of NXC. We initially wanted to use NXC for our tests then, but we thought, oh my god, NXC is crazy complicated. You actually have to write a configuration file to use it. So we came up with systemd nspawn, which is a tiny tool which takes very little configuration. Like in most of the case, you can just invoke it, and it will do the right thing and start a container with a complete operating system inside of it, right? So for us, it was primarily originally a testing tool. Like the man page until recently even said it's about testing, building, profiling, and these kind of things, but not actually for production. We removed that actually recently because if you know Rocket, you know this Core OS container manager, actually the lower level building block that's actually using for the container stuff, the lower level container stuff is actually systemd nspawn. Or I probably should point there. I have those screens over there, so I'm sorry for that. So the lower level building block of Rocket is nspawn now. Unspawn is like, it's much simpler than LXC. You basically just point it to a directory and it will boot up the container and you just run. And that container can run a full init system, right? Like we actually made sure that, like, we didn't want to really define a new container format like Docker or Rocket was doing. So what we focused on is really just make it boot the container formats that already, like the image formats that already are standard. And those are, of course, like raw disk images, like how you would boot them as KVM or on physical, like you could write it to USB disk and boot it on a physical machine. So we made sure that this container manager can actually deal with disk images, right? So you can just point it to something that would otherwise run a key move. And we'll boot that up. It cannot deal with all images. Like some images require specific hardware to be around, but in containers, you generally don't have hardware because the Linux kernel doesn't virtualize hardware for containers. Probably shouldn't. But many systems actually just work like that. So you can, what was essential for us basically is that you can have by default images that boot up on a real system, like physical system, that boot up in KVM, and then boot up in this container manager. And you can have full portability. So you can choose whatever you want to do. Systemd nspawn is actually really powerful these days. Like it's basically like if you want to compare it with other implementations like Docker, Rocket, LXC, and things like that. But for us, systemd nspawn is basically the low level bit. It feels a little bit like the QEMU binary, right? Like what QEMU does for VMs, systemd nspawn does for containers, right? It just does a lower level thing. And the same way as most developers will probably, as most people who actually deploy VMs will actually never really manually start the QEMU command, right? Like to deploy something in service, use something higher level, use OpenStack, open whatever, or libvirt, and all these kind of things. The same way, like in systemd nspawn, that needs to do something that's built on top. For example, Rocket does that. So yeah, to give you, yeah, it's like QEMU KVM, but just the same thing for containers. And Rocket is built on it. It's supposed to be really simple, right? Again, you can just point it to a directory and boot it up. No configuration necessary. But it's all powerful, right? It's the binary has a lot of switches. We tried really hard to make this switches simple to use. They are relatively high level. They're not as low level as LXC. Like an LXC will dump a lot of information, a lot of concepts like namespaces and C groups on you. Nspawn is much more high level and tries to make use of namespace and C groups, but give you much higher level access to them. Yeah, it does all kinds of things nowadays. It even does user namespacing, networking. It has hookups. Like we made sure that networkd works really nice with it in a way that if you run networkd inside of the container and run networkd outside of the container, then they come with default configuration. So that if you have a virtual azimuth link between the container and the host, it will actually automatically do a DHCP and things like that. Like networkd can, by the way, also do DHCP server stuff, DHCP client stuff, and it can also do like minimal masquerading setup. So we actually adjusted all these other components of systemd so that it integrated nicely with nspawn, so that you get the networking set up automatically, right? Like so that the networkd and the host does DHCP server, automatically picks an IP range that is unused so far, and the network key inside of the container then does a DHCP request and gets that information. It's it's all work in progress, right? But right now we already have really powerful setup because network D on the host will also do masquerading, so that you actually get without doing anything. We don't have to configure anything really. You get a container that can connect to the internet, but lives in its own virtual environment. Ansible can do lots of other things. Like just check out the man page. Can automatically add the virtual element that it does to Ridge and whatever else. It's really awesome. And there's another component called system machine, which is closely related to nspawn, but it's basically for us. Nspawn is the way we see it is that it turns containers into normal services, right? So which is different, for example, for Docker, right? Like in Docker, you have the central Docker daemon, and all the containers are forked off that, right? In systemd, we just say, okay, containers are just special services, right? Hence, they run, if you run 5 containers, they just run as 5 individual services. And you can, if you want to make changes to your system service and set properties on the system service to limit memory, limit CPU, limit whatever you want, you can do it the same way as you would do it for an Apache instance. You can actually do it on an Ansible instance. From systemd's perspective, there's no difference there. Systemd machine D is basically then a central component that virtual machines and containers can be registered with, so that the rest of the system gets to know about the concept of what a container actually is. The background of that is that we actually think it is essential that the core operating system knows what a container is, it knows the concept of a container from all layers of the stack. By registering, nspawn will register automatically all its containers with machined, but actually it's open to other implementations as well, right? For example, LXC, libvirt LXC, the container implementation of libvirt, you registered it with as well. By registering it, you get a lot of functionality, for example, PS, the Unix PS command that shows you processes. It gains support for having a column where it can show you to which container does a process actually belong, right? And that works by registering it with machined. It also, machined will give you the functionality automatically that every container that registers with machined will automatically get hostname resolution for that container, right? So if you have a container foobar running on your system, right? Simply by registering it with system machined, you get hostname resolution so that you can locally resolve the container name, and it will automatically return whatever IP address is currently configured internally in the container. So, and then there's a couple of other things like that, system, what's called system monitor will show you the machine as well. And then all of these tools like system control, journal control, and so on, they have this -m, -m switch where you can specify a local container name, and then they will apply the operation that you want to apply, not to the host, but actually to the local container by that name. And there's a tool called systemd run, which is actually really useful. It basically allows you to run any kind of command as a service, just by typing that on the command line. I want to run user bin foobar as a service, and then you type that and type enter, and there you have your service running in the background of that command. But it also has this -m switch, which basically allows you to run any kind of command you want in any kind of service, in any kind of container that you have running. This machine is basically this registry of things, and then we use the information that we have there to integrate with the container concept with the rest of the system. And system control actually has even this switch called system control -r, where it will not just print you the list of services that are running on the host, but it will descend recursively all local containers and will also show that. So that's a really useful command if you want to know what's actually going on in your system, right? Because the idea there is that, the system is probably not just the services that run on the host, but all the services that run the containers as well. The concept of having containers so deeply integrated into the operating system that all the commands understand the concept of this is actually not new, right? It's what Solaris did with Solaris Zones a long time ago. Like in Solaris Zones, you had this SVC control, something was called, and a couple of other commands that understood natively what a container, they call it zone, of course, actually was, and you can apply the commands to just a specific zone instead of the host. And yeah, with systemd, we try to come up like, again, Solaris is a big inspiration, I guess, with something that way. And again, this machine is open for every container manager, and many container managers actually do integrate with it. And you get this function. And we're working on adding more integration. Machine control is the command how you can actually interface with systemd machine. It has commands like systemd control, machine control status to show you information about the container, machine control stop, and whatever. You can actually use it to bind mount stuff from the host into the container, to copy files out of containers. It's a very powerful tool nowadays. And again, because it works for every single container that is registered with machined, and those containers are the ones that nspawn creates, but can also be the ones that any other container manager that decides to integrate this machined implements. Here I kind of already mentioned that you have integration with PS. System control -m, I mentioned system control list containers actually gives you a list of all local containers and shows you the health status of the systemd instances running inside of them. So it's a very high level thing, right? It will just tell you, okay, in this container there's 1 failed service, or in this container there are 5 failed services, or in this container everything's okay. System control -r, I already mentioned, is like this recursive thing that shows you the entire list of services running on the system, on the host, as well as in each container. Login control -m shows you who's logged in, what seats, what sessions, whatever exists in a specific container. Systemd run -m I mentioned. You got the roast and resolution. Then actually the definition of container we also did on other levels of the operating system. Specifically, we have these APIs called, like the C API is called FDBus, which is an implementation of a dbus client library. From the base on, it knows the concept of connecting to a bus, not only of the local system, but of any local container as well, right? Which is actually what we built tools like system control -m on, because system control will basically connect to a bus, look for the systemd service on it, and do some operation on it. And by having the support in the dbus library that we use for that to connect to a local container, we can make all these clients just work for context as well. And SDLogin is another API that we have. It basically tells you, I guess it's a misnomer these days, but it has APIs that you give it a process ID, it will tell you to which service it belongs, to which user session it belongs, to which user it belongs, to which machine it belongs, like container. By the way, and to clear that up a bit, when we use the term machine in systemd, we use it as a generic way to refer to both VMs and containers, right? Where VMs is something like KVM, like where you actually emulate hardware, and containers where we don't emulate hardware, but where you share the same kernel, right? So, I mean, the nomenclature there is a bit weak, I think, because, I mean, Intel, for example, does this clear containers, which confuses everything even further, because suddenly they refer to full hardware or hardware virtualization to something that they call containers. But anyway, it's really confusing. But in systemd, we try to stick to the naming that VMs is KVM and things like that, and containers are nspawn and things like that, and machine is a generic term for both of that. And then I think that might be one of my last slides actually. Systemd import is something. It's another demo that we ship. It basically allows you to download images from container images from the internet, to use them with nspawn in a nice way. It's actually a really useful tool nowadays, because it basically makes available containers in 3 different formats, right? Like you can download a tarball, like tar, gz, or whatever tar compressed thing you have. Then we'll decompress it, put it in virtual machines, and then it's there, and then you can actually point nspawn to it and boot it. It also supports, as I mentioned earlier, this thing where you can download disk images, right? Like these disk images that sometimes have the .img suffix. It can also deal with, what's the thing they call the cumulatives, like the compressed ones? Those are like the ones. Sorry, what was it? Yeah, it supports QCOW too, right? Yeah. And you can download that so that you can start that with Spawn. And it's really nice to use, right? It's like the client side for it is also machine control. And you can just say machine control pull tar or something, specify URL, we'll download that. We'll actually do GPG verification, which is really useful. And basically, the idea behind that is we really didn't want to sit down and come up with a new container format, so we just used what already was there, and those are tarballs and these images. And it's really cool because you can actually use this tool to download the normal Ubuntu cloud images because they're shipped as tarball and as disk images. You can use the Fedora disk images. You can just, like the ones that already are there, and instead of running them in KVM, whatever you want, you can just run them in container, which just work. Ironically, even though I work for Red Hat, the Ubuntu images are actually better integrated right now because they got the GPG signing right. So they actually have they put the images up on their service in a way how the client can automatically know which file it needs to look for to do the GPG verification, and the Fedora people have not been capable of doing that. So they basically named the GPG verifications, like the signature file, completely randomly for every image, completely different names. Sometimes they call it foobar, and sometimes they call it Maldon, which makes it impossible to do that automatically, but we are working on with the Fedora people to actually fix that. Or actually, I'm not working on them, the Fedora people are working on that. But the idea basically is that, yeah, to put this all together, what nspawn, machined, and ipd are, like if you want to compare it with something like everybody heard here knows what Docker is. Nspawn is much more low level than Docker. And then import D and machine D are basically something like, you know what, Docker has this concept of having microservices inside of each Docker container, right? They basically say, yeah, you don't run systemd in a Docker container, is basically what they suggest. For us, it's like, we think that the difference between a container and a normal system, like a real host, should be minimal, right? So you should have the same APIs available, the same things on disk available, the same semantics of things on disk available as on the host, right? And then for us, that means basically that, yeah, we should focus on doing systemd inside the container and on the outside. I mean, what else would you expect from us in a way? Like for us, of course, systemd is the center of the world. So that basically means, yeah, we say run on the host end. Yeah, just to give a bit of an idea where the differences in the where we want to go with Nspawn. I don't want to be in competition with Docker, to make it very clear. So I really do not want to focus in that territory and do with something with microservices. I just think that container technology is cool, and that container technology should actually just be able to boot normal images that we already have, where they already have millions of tools like Vagrant and whatever they're called, and just yeah, be a more lightweight version of KVM and a more integrated thing, right? Like so that you're like I call it integrated isolation, right? So that on one hand it's isolated and you get all the separation. On the other hand, it's much more integrated than KVM is, because things like recursively entering into the containers to get the list of units is something that is very hard to do in VMs, right? Because you actually then would have to go over the virtual network, and that's annoying. Or things like, you know, journal control actually has this wonderful feature. We specify journal control -OM, and it basically will generate a single series, like a single stream of log messages, where all the log messages from the host and from the containers, like all of them, are interleaved in one single stream by date, right? So, of course, it can sometimes be a bit slow to run that tool because it will go into every container and try to get the file. But it's really useful if you just have a couple of containers in your system, you want to figure out what's going on, and you not just care about the host, but also about everything else that runs in the system. You can just type journal control -M, there you get one stream. Yeah, for us, it's like this way of integration is something we can do with containers. We can't do that with VMs, and hence, yeah, that's why we see this as different. Because I mean, of course, on containers, you always have access on the system to the file system of the container, right? You can always send a container, pick it up. In the app, that's much more difficult because you actually would need something like Samba or something to connect. So yeah, that's that stuff. I think I'm mostly out of time. I think this one is actually my last slide. I think we should start with Q&A instead of showing that thing, because I mean this slide just contains completely random features that I also thought about, but it's actually mostly about filling time. So really, I mean, there's so many things in the system we talk about. So I try to focus on the generic stuff, and then these are specific features that I think are particularly cool about system. Actually, about some of them I already talked about. The everything is locked thing I already talked about. The quota collection I already talked. And there's all like talk about things. Anyway, so let's go to the Q&A part, and I hope you all have a lot of questions.
Yeah, so there are the 2 microphones here. Please, anyone who has a question or anything they want to discuss here, please come on up and get it going. Really? No, nobody. There we go. Sean, thank you. Get started.
Okay, so you're changing the way a lot of, you're messing with stuff that hasn't changed for a very, very long time. Okay? So people that learned Unix like 20 years ago, right, are used to interacting with things that are being replaced. So I guess my question is, what do you decompress after a long day of being trolled by crazy people on the internet?
Well, with this, of course. Well, I'm German, we drink a lot of beer. We have good beer there. I don't know, I mean, the general answer is like we always wondered like why we actually managed to push through with systemd, even though other people didn't, right? Like, I mean, the entire concept of doing a new init system isn't something that we came up with. There were many attempts before, like init and all these things. And I think part of why we managed to push that through is because the people involved, like initially it was just Kai Sievers and me. We are weird in a way that we don't feel too much like if we get those insults, and we got a lot of them, and we got death threats and all kind of bullshit. It's like I don't know, like most people will probably, and most people tried that before, just give up, right? But for some reason, we don't care. I don't know. It's like we care about people who we respect and their opinions. But if there's some random idiot on the internet who thinks it's fun to collect bitcoins, then it's like whatever. You're an idiot. I don't care what you have to say. I think, I mean, it's actually a really interesting question. Like if you do open source, like it's something. I mean, you know that what happens at it's sometimes not a very happy place. So better get it fixed again and deal with that stuff. And we have that, and so we mostly fixed everything by drinking beer. And everything was good again.
So over there.
I know you covered this a lot in the past, but the main criticisms that I often hear about systemd is the sort of the monolithic nature of the project. And I've seen you, the monolithic nature of the project.
What is monolithic?
And I've seen like you rebut that by saying there's lots and lots of little individual tools. But I think the way this comes up in practice is the tools are very tightly integrated, and it's more difficult to use some of them and not others, or to replace some of them with competing products. So can you speak to whether those concerns are founded, or how you handle that type of criticism?
I generally think they're unfounded, right? Like but I mean, it boils down to a couple of factors. Like one of them is like I would define modularity differently than other people do, right? Like other people think they should be able to use like network D, for example, without using the rest of the system. That's something that I'm not interested in. Like, I mean, it's not a priority for me. I don't care. Like, it's open source. People can do whatever they want, but it's not at the top things that I want to do, because the way network D works, it talks to lower level parts of the operating system. It makes assumption how the system is set up, right? So, like for example, simple things like /run. Like /run is something we in the systemd team pushed through into all distributions like 4 years ago or something. It's probably 5 most of you don't even know about it anymore. But it's basically on older distributions like RHEL 6 and things like that, you have this runtime directory in /var/run. And we said it needs to be run because of various reasons during boot up. And we make the assumption that it's there in the network D. And if we suddenly would deal with having like lots of different init systems that are below what we're running on, that set up the system differently, that mount C groups to a different place, and that set up these things, that do not have these libraries, do not know the concept of services and these things like that, And it basically means that we have a lot of burden of keeping things abstract and having to care, like having to have it like this layer of abstraction in place. And it would
Those that push the burden and the layer of abstraction up to your customers, the people who have to maintain software that runs on different types of Unix, that runs on different distros, they have to make a big switch to embrace all of systemd at one time. Even if they want to do that because it's lots of good features, it's still a flag day that they have to manage with their.
Well, the way I see it is that systemd is really the basic operating system. Like it's part of the basic operating system. It's not something. It's not an app, right? You install stuff. It is something that the operating system vendor has to integrate for you, and it's really not up to the users so much, right? Like it's really about the vendor, right? And they basically need that
the developers of the software you're trying to run, right?
It's basically like for example, I mean, if you buy RHEL 7, right, you get systemd. That's a deal, right? But you don't it's not really supposed to be something that you add on later, right? And so I don't know. I can see that people don't like this thing, right? Like the fact that we do it that way. But I mean, if you look at it from our perspective, we want to keep our code minimal, right? And we want to be able to just call lower level functionality. Like, I mean, after all, systemd is really low level component, right? It runs as first thing after the kernel started. It's as low as it gets in user space, right? So we want to be able to just use kernel functionality. That's it, right? And if you actually care about the portability, care about the portability between different kernels, care about the portability to run in different combinations of software, then you suddenly need to deal with so many variables. It's about it explodes the test matrix, basically. And it's not a priority for me because I mean, like for me especially, like the Debian people, when the discussion was going on with Debian adopting systemd, like one of the major complaints was it doesn't run on FreeBSD kernels, right? For me personally, I think it's a completely crazy idea if that would be, because would the FreeBSD people ever adopt systemd? No way, that's not going to happen. I mean, just think about that. It's a completely ridiculous idea. I mean, if you look at how Solaris solved it, they came up with SMF. Is SMF portable? Inherently not, because SMF uses the concept that their kernel introduced, they call them contract IDs or something like that. That's how they keep track of the process that belongs to a service. And it's like, I don't know, I think it's the idea of making it portable is it's a burden for us for no real value, because the only people who will ever make use of that are really the Debian people who think that it's a good idea to be able to use the FreeBSD kernel with the Linux user space. And quite frankly, if you look how many people have installed that combination, it's probably less than in this room. Right? So I don't know. It's like for us, the priorities are different. And if you look at the other side of the medal, the benefits of not being portable, of not supporting all kinds of combinations are our code is more minimal, and we will give you right away much of the power of the Linux platform. Because for most of the history of Linux and of Unix, it actually was that nobody was using the Linux functionality so much. All the programs were developed against POSIX, and POSIX is an API that's really, really it's not what we do nowadays, right? And with systemd, we think, well, the functionality exists in the kernel, and it's awesome, like Sequence, for example, and you should be able to use it, and we shouldn't try to hide that stuff, we shouldn't try to abstract that stuff, especially since in many, many ways, it gets really, really complex to abstract these things. Like for example, systemd has this concept that you can actually lock services into sandboxes, right? Where you can basically say, okay, Apache shall see the system, but it should only have read-only access to /user, which is it's a policy that probably everybody wants, right? Because if somebody exploits, but things like that, they're inherently bound to being able to mount namespaces the way Linux does. Something like that does not exist in FreeBSD. But then, of course, people on the internet claim, of course it does, there's jails, but actually jails are very, very, very different things. So, I don't know, it's it's a huge burden. You should not underestimate the burden of making this promise that our software works in all combinations on kernels. It's a promise that we can't make without lying, and it's also, I think, it's not interesting. It comes it makes other things worse. It makes things. So I think it's modular in the way that, yeah, you can turn off most of the functionality of systemd, like most of the components except for 3. And you cannot like use much of the functionality of systemd outside of systemd. But I think it's pretty easy. Also, that's just what we say how to use it, right? It's free software, you can do whatever you want, right? And then people do that. Like, for example, Rocket, which uses this nspawn thing that I was talking about. They actually wanted to make sure that Rocket still runs on crazy Ubuntu versions that have not switched to systemd. And so they just did, right? Like they just took nspawn and said, okay, let's modify a couple of things to make it work. And actually, I merged those changes that they asked for upstream even because they were okay and didn't comply. But of course, I always make clear that even though nspawn works on non-systemd systems now, it's nothing I want to support. I will always point people to CoreOS to say, that's your problem, it's not mine anymore. But so I mean, it's not even that because we are evil, right, that we do these limitations. It's like we were nice to CoreOS and merged the changes, even though I don't give a crap about the idea of making it portable. But it's really about keeping things maintainable for us and minimizing the task metrics. I hope that makes sense. Another question?
So as someone who's drunk the systemd Kool-Aid and has been working on a lot of unit files lately, is there any way to switch systemd into kind of a developer mode where it uses iNotify or FAM or something to watch unit files as they change? Because that's something that I found really frustrating, that every 10 minutes I'm having to reload systemd to reload the unit files from disk.
Yeah, that's a request we actually get often, but I think it's inherently not possible to implement something like that safely on Unix. The reason for that being, like, just think about that. You have a unit file disk, and then you rename it, right? So let's say we implemented this in my notify thing. System, you would notice, oh my god, the old file is gone. It would start unloading that, right? And would go through the directory again, trying to find the files. Now, depending, like it's racy, basically. It can happen that as it goes through the directory, it can happen that it will see only the old file. It will see only the new file. But what's much worse, it can happen that it will see neither, or it will see both. And that is a problem, right? So Unix does not have a transactional file system. That's basically what it does.
And maybe I'm not looking for all of systemd, but specify, hey, I'm modifying my unicorn unit file, trying different environment variables and tweaking all sorts of different things. Is there a way for me to set it so that, okay, every time I write unicorn unit, reload it?
So basically, I mean, one of the reasons why the system control edit command was added to make this easy for you, because system control edit will create a unit file with .vim on it or whatever other editor you have, and then we'll do system control demo reload automatically to make this easy for you. But it's like the way how configuration works on Unix is that the iNotify stuff is not a good idea, because you always have this thing that, like look at debug configuration, Apache configuration, they also always have a ton of different files in the directory. And you cannot automatically get a snapshot that is in itself consistent of what's actually on disk, right? And then the way how Unix solves this problem is by making it explicit. That you say, okay, make these 5 changes, remove that unit file, rename the other unit file, add something to that unit file. Then you tell system you can now reload it to get the full idea. That's how Unix works. I mean, if you want us to fix the iNotify thing, which I would be open to, then it basically would mean you would have to add the transactional file system to the Unix so that you can do that. But I think that's pretty much not going to happen. So.
Okay, thank you.
Did I hear you were a Emacs user?
Mm-hmm.
Oh, that explains a lot.
I'm also a Vim user. So I use both, like for small files, Vim, for big ones. But yeah. Does that explain anything more?
You're fine, I get it. It sounds to me like a lot of these accessory services that have been added, while they're useful, are sort of like a trust issue. Because the resolver functionality you described, that's a libc responsibility. That's like RFC 6724. Or your etcgai.conf if you guys are familiar with get at or info. And then the SNTP, the timesync. SNTP, I agree with you. In most cases, the client doesn't need full NTP implementation with a real-time clock, but it needs SNTP But why integrate that into system D? It sounds like you don't trust the rest of the operating system, and that's why you're implementing turtles all the way down.
No, I mean, the reason why we implement that in system is because we think that they are inherently, should be part of the operating system, and because individually, each one of these are not, like, you know, if they look at the NTP implementations like one source file, right? You can read through it, you will understand it. So it's like, something that we saw with system is that an operating system should be much simpler to put together, right? Like it should be like 20 components. It shouldn't be 300, right? Like with what it currently is. Like if you build basically a minimal operating system together with classic Debian from 2 years ago, right? That does NTPs, that does network configuration, you need 150 or something packages, right? And we think that a lot of that is like completely pointless. Like for example, like NTP, for example, yeah, sure, we could have done outside of systemd, right? But the way, because we can do it inside of systemd, we can share so much code with the rest of systemd, because like we have basically a gigantic library of helpers for us that make it very, very easy to write daemons, to write system code. Because that is that way, it comes to it results in timesync DB with a very short piece of code, right? Like, but it's like, it's really not about not trusting people. I mean, we trust Linux kernel, we trust a lot of other things. It's just about, we think that some functionality just should be part of the base operating system and should be much simpler than what people sometimes use, right? But it's like, I mean, if you look at the journal, for example, we saw so many issues with classic syslog that we did it, right? That we thought, okay, we fix it. And it's not even that we did that without consulting with the syslog guys before, right? Like for example, I sat down with our syslog guy back then and told him about like a lot of things that we wanted to do, and told him about things like for example, on Unix, like on Linux, you have this thing that you can, for every log line that comes, you can get the UI pit and stuff from the kernel. I told him about that. He actually added that functionality, but he also didn't really get what we were doing, right? Like he didn't find that interesting. He found other things much more interesting. And then after a while, we just said, okay, we still believe that that logging needs to be absolutely essential part of the operating system. So we should do it, and he's not doing it. But it's also something about ordering, right? Like because like in the special case of syslog, for example, because we had this goal of that everything's logged, we needed a logging demo that actually can run in the earliest boot, right? That can run in the Android even works. That's something useful. But our syslog and all the other implementations are not like that, right? Because you need suddenly a lot of integration to the basic system. Or the other reason, like if you want to connect every daemon that runs with the journal, right? Every std out, stdr of every daemon with the journal, then you actually, like, that's a very low level interface, because it's like, you know, the earliest processes that we start on the system need to hook into that kind of stuff. So it needs to be, the service needs to be written. It's PID1 basically that forks up like a little process that it's still part of the code base of PID1 that actually then connects to that logging stuff. That's so low level integrated that you cannot really do that externally. I mean, of course, you could do that if you would define really low level generic interfaces and things like that, but it becomes like you actually don't want to do that, like define these generic things. But it's like, I don't know, it's like for us, it's like, when we come up with these things, we do this because we inherently believe, like we think a lot about it, we inherently believe that things need to be different. And like, I mean, but it's like, it depends even on the subsystem. Like for example, console kit, right, which we replaced with logging, is something where I was sitting down with the original author with console kit, like John McCann, a long time ago. He was a good friend of mine, right, and we were talking about it for a while. Actually, I wasn't a console kit maintainer myself for a while. And we saw, okay, that's an issue, that's an issue, that's an issue, that's an issue, and we want to deeply integrate it to the operating system so that the tools that we have actually know what a session is and things like that. And so we decided, okay, we'll do a new thing. We'll do it inside of systemd, and we'll can make use of the concept of systemd exposes. Like this goes down all the way to, like for example, C group integration systemd you have now, right, which basically allows you to set resource limits on services, but it also allows you to set resource limits on sessions of users, which is an incredibly useful thing, because you basically can say, yeah, if I log a user then logs in and give them so much memory at max and bind to this CPU and that CPU and only so much CPU at most. But this kind of integration you can only do if you explicitly bind it to systemd, because without systemd you don't have the concepts of resource management, of C groups, all these kind of things, right? And for every single tool that we added there, we had these reasons. We saw that the previous thing was not good enough, that we need to have the deep integration, like if it's a journal, if it's a login, and that we wanted to keep it much, much simpler. Because, I mean, what you should never forget that if you have Unix standards, like classic Unix standards, they do a lot of stuff over and over and over again, implemented by different programmers in a different way. Like it starts with a system 5 init script around it. Like there are some init scripts in this world which are well written, but there are also numerous init systems which init scripts which aren't, right? And they copy the same code over and over again, make the same mistakes, they work in weird ways. And that's actually quite some amount of code in there, like with the double forking in the C code of the daemons and things like that. So what we wanted to do is that for our own daemons, we can remove all that and replace it by generic implementation, but minimal, and we don't keep duplicating ourselves over and over again in a crappy way, right? So yeah, it's about sharing code. It's about integration that we saw as really useful. And it's about that we saw that for those components, the implementation that everybody was using were not the way we thought this stuff should be looking like. I hope that's a bit of an answer.
Given that you're doing a lot of networking and a lot of name resolution things, and I was wondering if you were thinking about, and also machine management, I was wondering if you were thinking about cross-host machine management like Fleet.
So that's a very good question. But so far, and I'm pretty sure it's probably going to stay that way, is that we always thought that what we do with systemd should focus on the individual system, right? And it should not be something that you manage a cluster with. It should be something. If you want cluster management, it should be built on top of systemd, right? But that's true, for example, for nspawn. I think like if you use Rocket on top of nspawn, it's perfect because nspawn will just do the individual thing. But Rocket then provides you with the way how you can deliver it across machines and distributes the images across machines and things like that. And that's kind of how I like it to be, right? So that yes, we will provide you with a lot of APIs that you can build on, but it's somebody else's job to build on that and turn this thing into cluster stuff. Well, we are good friends with the Chorus people, and I really like that they did the Fleet thing, and I'm pretty sure they should stay doing that, but I'm not sure I want to be in that area.
So I just had a quick question about, I guess, journal control, and how closely do the logs spit out of journal control follow, I guess, like syslog output? And then also, what would you recommend for the time being before I saw there's, I guess, journal D possibly being integrated by spitting it out into other possible formats, other services? What would you recommend for the time being if I wanted to say journal control -f, pipe that into a file and then follow that?
So if you use journal control, by default it generates something that is very, very close to the classic format. But it does have some improvements. Like I already mentioned some of them. It does coloring stuff. It does it automatically turns off the coloring actually if you pipe it, right? It does the thing. It will actually show you where new boot happened. Like it will basically insert the -- there, which you can just ignore, but right. And it will fix the time zone, like the timestamps for you, move them to the local time zone. But other than these little things, which I would consider compatible to the classic format, it should be absolutely the format. So basically, our goal there was that you can replace any invocation of cut varlog messages with journal control, right? And it will generate the same output. Journal control can actually generate that output, and it does that by default. And it has -o. And with -o, you can choose between a couple of other formats as well. So there's a JSON format, right? It will generate that, and then you get the structured data. Because, I mean, of course, the classic syslog one will not give you structured data. There's one that's called verbose, which gives you basically all the fields that there are. There's a couple like this. One that just gives you the messages and strips away all the other stuff. There's an export format we defined. The export format is basically, it's a binary serialization of the journal stuff, because a journal can actually contain binary data. Right? It's not just ASCII text. It actually can stick coordinates and really crazy stuff into the journal if you want to. And the export format will deal with that, right? Like, because, I mean, if you export coordinate as JSON, you will go crazy because it will turn it into a byte array and then you're like, blah. The export format is very simple. It's documented. It's like we have put it together. So if you want to implement it, that's one way. But it's really up to you. Also, when we ship a little tool, like a little service, it's called Systemd Journal Gateway D. It's turned off by default, and it talks HTTP, right? Like, I mean, it's an entire networking story about the journal, right? Like, because of course everybody uses the syslog protocol right now, but we also think that the syslog protocol for networking is awful, right? Because it's lossy, it's not encrypted. I mean, there are ways how you can encrypt it, but nobody uses that, right? And it's not a nice protocol. There's no way you cannot parse it, right? Like, because everybody interprets it differently. And then when they wrote the RFC, it was basically 20 years after they designed the thing. But like, I mean, if you can call it design. So with the journal, we started playing network is essential, but it should probably not be the classic BSD thing, because we did not want, like, if you look at the sources of our syslog, they spend a lot of time in normalization and things like that. We don't want to have that in our basic tool set. So what we said is, we also don't want to come up with our own protocol, so let's just use HTTP. And it basically gives us a lot of things for free, like SSL. It gives us, it actually allows us to implement both a push and a pull model, right? So, I mean, classic BSD syslog is, of course, always a push model, right? You push out the messages as they happen. But we also saw that in many cases, it's actually much more interesting to have a pull model, right? Like, if you have an embedded device, or even if you cluster systems, because, like, if you have a cluster of systems and all of them always write the BSD syslog messages to the central server, and then somebody nmaps your cluster or something like that, and every single system generates one log message at the very same time, then you bombard that syslog server with a gazillion of messages and it will go down, right? So we saw that inherently for many setups, actually pull model is more useful than a push model, but where basically the central server would just pull the stuff out of it. So yeah, you basically have that, and that can also generate like 8 different formats. Like, it can generate the classic one, like the classic syslog one. It can generate lots of other like JSON one. And yeah, it's actually really useful stuff. Like, our intention there is really that people who use higher level logging stuff actually use that stuff to pull out or get the traffic there. Then that protocol is actually used. We have a tool that allows you to sync logs across machines, so that basically use that protocol. It's general remote or something. And then basically, it will write back into a journal file that we can then use, things like that. So yeah.
So first of all, I just wanted to say, like, I think all the design decisions that we discussed, for me, they make a lot of sense. I just want to say congratulations for what you have achieved.
Thank you very much.
The reason probably being like, because I'm not an expert, so I can understand the pain of the sysadmins, because they can hate me for saying that. But I think it's a good thing to start fresh, like from a new code base, and it always makes sense to like progress. My question is around, like you mentioned briefly, there's like mount like units and how they actually interact with how you can use like with a traditional like FS tab. Can you elaborate on that? Like,
yeah. So Systemd actually supports FS pretty much the same way as System 5. I mean, with some changes, but it pretty much is supported right away. So in Systemd, there's a concept called generators. Generators are basically something that are basically small binaries that we execute very, very early in boot up, and which convert configuration from other formats into system units, right? And there's one generator which is called system DFS generator, which basically reads that STAB and turns it into, like we had it on the slides, right, like the mount units and things like that. So that's basically how you get the integration of STAB, FSTAB. Like if you then use commands like system control cat or something, you can actually look at the unit files it generates and will contain comments like that actually comes from that FSTAB file.
So you'll still be reading the FSTAB file and then you use like the generate the units out of that FSTAB file.
Yeah, that's basically how we do most of the compatibility. We have one generator that reads FSTAB and generates mount units out of it. We have one.
Like directly a unit file for the mount, like not bother with.
You can do that too, but it's like I mean, usually I would tell people that there's no reason to, but you can just write it into FCF because FCF is a very condensed way to run things. So it's not bad in any way. But you can also write it as mount files, but I'm pretty sure that mount files, I mean, they're always longer, right? Like, I mean, there's no lying about that. It's like, they're more
there was some, like, the reason why I'm asking is, like, on Arch, there was some issue back, like, 6 months ago or something. The system was not doing the timing properly, and it was hanging the system on Arch. So that's probably, like, I was thinking, like, so now we just, like, manually mount the file system, not like keep it in the FSTAB. So I was wondering if like doing that directly in a unit would actually improve something that like we can get the dependencies correctly or something.
Well, I mean, like system actually gets the units, the mount units, not only from FSTAB but also from what's currently mounted and things like that. And we really try to make sure that we stay somewhat compatible to how things were done before. And to not annoy the user, right? Like, so if you actually use a mount command, like on command line, it's completely fine, right? Like, system will take note of that and try to make sense of it and integrate it into the unit file tree. So there's no need to actually always write mount units. And if the FSTAB generator was broken, then that's a bug, of course, and we should fix that. I mean, to make this clear, we do not provide 100% compatibility with the old FSTAB. We only claim 99%. The reason for that being that, well, FSTAB used to be something where you wrote in order what you wanted to apply, and then mount-A would actually mount the stuff in precisely that order. Like it would mount the first thing first, and would go to the second, mount that after the first one was over. In system, that's different. In system, like with the dependency tree, we actually mount everything in parallel, right? Modulo, where we can't. Basically, so basically, if you have something like you mount var from one partition and var temp from the second one, of course we need to mount var first and temp second. Or if you have a bind mount from /foo to /var, then we probably should mount foo first so that we can then bind mount foo to var, right? And that has effects, right? Because sometimes the dependencies are not obvious.
I think that was the issue.
What's that?
I think that was the issue because probably like it was an external RFS file system, and he was like trying to mount before the system. Like,
yeah, like for example, one of the things where it all falls flat is if you use something like the new overlay FS stuff, because on the overlay FS stuff system you doesn't know, but the things that you overlay on top of each other probably need to be mounted first. But the way we solve that is that there is a way how you can, in CFS tab, you can specify additional mount options, like they're called x-systemd dot, where you can specify additional dependencies that systemd will honor, right? So basically it's the way, like systemd will figure out a lot of stuff for you, but if you then start to use more exotic stuff like overlay FS, it might not get everything right, but then you can tell it explicitly by adding extra mount options there, and then we'll do the right thing. But we are aware that some setup program. I mean, it's a general theme that we try to follow, right? It's like we try to provide compatibility with what it was before, like System 5 in it and whatever. But given that we are not System 5 in it, we will never have 100% compatibility. But we try our best to document where we depart, right? Like there's a wiki page that lists all the incompatibilities basically that we have been aware of in the time, like when it was adopted Fedora and things like that, and what we suggest people do about it. It's really amazing what kind of crazy stuff people have done with System 5 init scripts. And it's like, I don't know, like, I don't know, it's just so disgusting. But yeah, so we will never climb 100% availability, only 99, whatever that
This
is.
is a real quick one. So with the release of System D 221, one of the first things one notices is you're not using semantic versioning. And not everybody uses semantic versioning, but do you have any, is there any particular reason why you chose to go with that integer release number?
So, well, it's a difficult question, but we try to, ideally, like if everything would work the way it should work, we actually would like to do a release every 3 weeks. We fail miserably at that goal, right? Like we want, basically, what we strive for is that we have a constant stream of small updates. And that basically means that you don't need, like we don't want the case where you add like 10 new features and redesign 10 things and then it gets a major number update. We really want to keep it like a constant stream of small updates. However, we're not good at that, right? Because it's actually a huge amount of work to do a release these days because like the project grew and like the amount of traffic we see on the mailing list, which we need to process, is immense, right? Like, and if we want to deal with that and actually care about the bug reports we get there and deal with all of them and fix them in the releases, then we actually need more than 3 weeks for each release. So, but still our goal is having a fast pace on releases and fix and fix and fix and fix. And then we also have a stable tree actually. So the idea is basically that the distributions, I mean, again, systemd is something that probably should never be something that people install. It's something that distributions built into the distributions and the people install the distributions, right? And the distributions will usually pick one specific version that they stabilize on. And then we ask the distributions to backport the patches. We will help them with that. Like we will tell, I mark basically whenever I do a new release, all the patches, like all the Git commits that we think are worth backporting. And there's actually a team where people from Fedora and Debian and Arc, they actually maintain a stable tree. Like it's in the same GitHub thing. It's called systemd stable, where they do the backporting so that they can share the backporting work. Because they basically just pick a couple of releases of systemd that they think make sense to stabilize on, and then they keep backporting the patches all the time. But I don't know. So in a way, that's my answer, right? Like if you want more semantic versioning, you have bigger releases and smaller releases and backports and stability stuff. We do provide that in some way, but we also expect the distributions to backport work. It gets a bit crazy sometimes, right? Like the backport sometimes for some of the releases that people stabilized on, because we really try to keep releases coming all the time. Can be 200, 300 patches backports. And Visual Realm has like 300 right now, but actually I didn't look into that. But I hope that's an explanation. But it's like it's always difficult coming up with a scheme how to do releases for a project. I'm not claiming that our system works right now because it just does not, because we cannot keep up with a 3-week thing. But it's in theory that's what we want to go for. It's like, and I think we can get like the reason why we think we can do that is simply again because it's not an end user product, right? Like this is true. So everything that we do, we always say, systemd is something other people build this product from. It's not a product in itself, right? And as such, we think that it's a job of the people who build the product from it to make sure they are aware of the system stable tree, are aware of the backports that are necessary, and things like that. So we don't want to be the ones who are solely and only responsible for doing stability work. We think that a good chunk of that work needs to be done by the distributions as well, and that's that job after all.
So I think we've generally run out of questions. I want to throw out one of my own. In general, I'm under the sort of the opinion, impression might be a better term, that systemd's initial focus and maybe inception is much more from the point of view of, as you said, managing a SQL system. The thing that I'm more used to doing is managing farms of systems, large numbers of systems, cloud systems, whatever. And I find that most of the features that are, I think, of the most interest to you, the things that are genuinely interesting that you mentioned, actually don't contribute to being able to do the things that I do. And my main concern is not being able to actually simplify, because as you said, it's up to the distribution to do that. But I don't get to rely on my distribution doing that because they have a divided interest. The core of the system is not simplifiable once it's been given to me as an input, right? And I'm kind of wondering how your vision is of certain things that are in place now becoming legacy, old, passe, maybe. I mean, that's a bit more of a judgment call. But my real question is, at some point, do you have a notion of feature complete and then refactor the system so that it can be simplified, so that we can get back to systems that have zero overhead in terms of processing while it's not actually doing anything? It's not restarting a process, it is not doing other things.
But so first of all, I actually believe the system is simple, right? It is like if you compare it with.
Excuse me, but I am attempting to compare it to other systems that do.
Yeah, but compare it with Unix, right? Like to understand what a classic Unix actually does, you have to have 300 different components, right? And these 300 different components have all different code bases. They replicate a lot of stuff, right? They behave differently. They don't behave uniformly. They basically require you as an admin to understand a programming language called shell, otherwise you cannot really do much with it, right? So while it is certainly, like, if you know classic Unix and shell and all these kind of things, then you're already a very well educated man, right? And then if you have to adopt systemd, then everything is new to you and different, and you say, what's that? But that also
I feel like you're asking this in a way where my question is very specifically about the simplification of the system, not about, as I feel, as a bit of a straw man as to other components that, yes, can become complicated, but don't necessarily have to be. And so the question is how to make things simpler beyond what you see as simple, but simpler into what is less.
I think, I mean, if it's, well, I don't know what you mean by simple, right? I think, again, it's much simpler than Unix, right?
Less.
But if you want to have it smaller, right? Again, like of the components that we ship, you can turn off many. Like if you don't want login because you don't have anybody logging in, go ahead, turn it off, right? Like there's a configure switch you can do that, where you can ask your distribution to put it in different depth orders, so and then you can not install that stuff, right? You can remove a lot of dependencies. You also, even if you get the operating system from Red Hat, like RHEL, and it usually enables pretty much everything that system provides, right? You can actually go ahead and change what it does as well. Like for example, we have this command called system control mask, which basically is a way how you can tell the system to not only to really never ever start a service, right? Which is like, it's basically like system control disable, but on steroids, because you basically say, okay, never start that thing. Even if somebody asks for it, don't. Like it's basically like adding a system 5 minute script and adding x at 0. And that is high level supported, right? So you have this ability, you can go into the system, like either you can build your own system that's much more minimal, and we help you with that, this is with the configure switches. Or if you take the more complex one that RHEL gives you, you can still even this thing that we think and that Red Hat thinks that should really be part of the basic operating system, you can still say, okay, I don't want that, you can turn it on.
Well, I appreciate that, I think, but my question is more about the complexity of systemd, or the components of systemd being able to be turned off without having to redo it myself. Because as you said, I feel like there's a shifting line here where on the one hand, you're saying that it should be up to the distribution to provide systemd in a way that is usable. But I'm saying that for me, I believe that the way systemd is provided to the people who provide those systems doesn't enable them to give me what I want, to give me the choices that I want. Now, I could be wrong, but I would prefer to be able to experiment with that without having to rebuild systemd and without having to reinstall. And I feel that the issues that I'm discussing or that I'm asking about have to do with systemd itself and not with the services that come under its control.
But I mean, it's really the tool that you make, right? Like if you use a distribution like RHEL, you get everything, right? And what they support is like basically one kind of combination of RPMs. And you can also go the other way around. You can go to get to, and then you have really high-level friendly support, and you build it exactly the way you want. But it's like, it's not a deal that we make with, like that systemd makes with you. It's a deal that the distributions make with you. It's like, we provide a lot of hooks, how you can adjust it to what you want. And if your distribution doesn't forward those options to you, but takes them away from you, then it's something that you have to deal with the distributions. And
I'm really confused because I'm asking about how systemd can enable that simplification for me. And I feel like you're saying that because the current situation isn't simple, that it's not of interest for systemd to enable that simplicity in the future. I'm asking if there's a plan for that or a thought for that.
Well, I mean, again, I find the word simplicity in this context really
Less.
minimal or
Let's
something.
just use the word less.
Okay, but I don't know. We keep adding options actually to systemd to make more things optional. That's all we can say. But I mean, will the systemd code base grow? Yes, absolutely. The way we see systemd is that as computing gets more complex, systemd will get more complex. I mean, there's no way we will lie about that. It's like starting a system today is inherently more complex than it was 30 years ago when Unix was designed. There is no way around that. I will not lie about that. And if you want a systemd where you can turn off the dependency tree or something like that, we will not support that for you because that's not how systems work these days. Like you can make yourself believe that it works that way, and you can still go back to system 5 in it. But then I would really like to ask you to do that, right? Because it's not how systems work inherently.
I mean, again, I just want to, I feel it's a little bit unfair here. Like there's a straw man of system 5 init, and it being the only thing out there when there are multiple other systems that have done this. Certainly, you're familiar with Upstart, with OpenRC or whatever it is, with Runit, S6, Stage. There are all sorts of ways of supervising systems that provide administration-wise, a very simple interface to controlling things. And I feel like systemd certainly fills that role just as well. But it adds additional features that may not benefit the job of the person who administrates a large number of systems. And that's really what I'm trying to ask about.
But I mean, in general, I think again that the systemd is more or less minimal, right? Like, it's like, sure, it does more than this inner systems that you mentioned too. But I also think that you want that stuff. And if you really want to, for example, if you talk about like sandboxing for services, I'm sure that people sometimes don't want that. But I also think that in the interest for the distributions who want to maintain that shit and take back reports for that, I don't think it's necessary to turn that off, especially given that it has issues because suddenly the service files that you write are not portable anymore. Right? Because sometimes they do something different than somewhere else. So we should really be careful with these kind of things. I don't think that, like I think at the basic stuff, even though many of the modules should be modular, I think it's one of the things that we really should do is provide the same set of APIs, same set of behavior across a large number of systems. So I don't know. It's like if you're asking me whether we will remove features from systemd, some we do, like for example, since we have read-ahead and we removed that because none of us could maintain that. But in general, it will get more complex. There's no doubt about that. Sometimes we can make things simpler, but in general, they will get more complex.
Well, appreciate your answer. Well, and there's one more question that's come up.
It's not even a question,
it's
a final comment to this discussion is, it's also the beauty of open source software is if you don't like what systemd does, that's why OpenRC and Runit and SupervisorD and all these other systems exist. So if you don't like the way systemd does it, go somewhere else.
No, that's certainly true. And so anyway, I think we're ready. I think we've finished up with the questions. We have trivia questions, and given the number of things to give away, everyone has a really good chance of walking away with something. So let's get through it.
Okay.
So all right. First question. So the way we usually do it is you ask questions, and I will try to figure out who's raising their hands. I'm sorry, everyone, if there are some things blocking. So if you think that you're going to be doing the answers, please get within my range of vision. I'll try to call whoever's first. We're going to give away, I think, 4 hard drives, was it?
Yeah, I think so.
And we have a few books and vouchers over here. So let me actually put them all in one place. You can come and look at them if you get the answer. I'm sorry, I just Have them right here. All right, yeah, those are what we're gonna do. All right, first question.
So the first question is, like all of the questions that I have here are something you should be able to answer if you followed what I was talking about. So the first question is, which was the first Fedora version to adopt systemd as default?
I believe I saw your hand going up first. 15?
That's correct.
So over here. Brian, is there a chance you could help him out with looking at the stuff? Brian, can you help him out with the stuff, please? Thanks.
So should I?
Oh yeah, continue.
Okay, so the next question is, what is systemd's usual process ID? Wow, that's a good question.
Go right ahead, please.
Good answer. Okay, the next one is a really, really tricky one. And so it's a trick question. You really need to think about that. So what is systemd divided by systemv, as in systemd 5?
I saw his hand go up right now.
You're very good. That is the correct answer.
Take it away.
Oh, I kind of expected that nobody would get that. I'm amazed.
What was the answer?
So it's because of Roman numerals, right? Like,
It's a C.
you're very smart. But the next one is going to say the speed of light, because that's C, right? But
Well, we have so much stuff. Do you want to give him? Do you want to give him a thing? It's up to you.
sure.
All right, go take a thing.
So the next thing is, what's the name of the IPC system systemd uses for its client communications?
Back there.
Divas?
Yes, that is correct. The next one is, what's the minimal container executor shipped with systemd?
Over here in the black signature.
Correct. I should have made these harder.
I think you're doing a great job here. It's
The next one is, name 5 unit types.
5. All right.
But those are not unit types.
Okay, hands. Oh, you're in the back there.
Yeah, give her 4 out of 5.
I'm totally on board with giving it to her. How do you feel?
Sure, then go ahead.
Another one would be. I don't think it's fair for someone else to steal it from you at that point.
Here's a trick question. To which operating system kernels has systemd been ported?
Back blue.
That is correct.
I'm sorry. Yeah, go for it. Go for it. You also have a blue shirt on. I didn't realize that. I'm sorry. Go ahead.
But 0 is the correct answer, yeah.
Bingo.
Okay, here's one that you cannot answer, but I'll ask it anyway. In which city will the systemd.conf 2015 conference take place? Well,
Space. Are you asking does anyone have space for it?
No.
You're the orange shirt.
Oh yeah, you're cheating. You know that.
Okay, so are you disqualifying yourself?
Well, I mean, he's one of the sponsors of our conference.
Right, no, I understand because he kind of just waved it off. So are you giving it back to the?
That's not a city.
Okay, let's try. South America. Okay.
That's a very good guess, but it's not.
Okay, any more hands? Okay, right here.
No. No.
Keep naming cities, guys. This is a great geography quiz. Barcelona.
Oh, no, you can't think a bit. Yes.
I was
That's
gonna say
what
that.
All right.
Berlin.
So yeah, our conference will take place in November in Berlin. It's not official yet, like we haven't put up a website or anything, but we have sponsors at least, and we have a venue. Oh, by the way, like over there, I never mentioned that, Daniel Makovic, another systemd hacker is actually sitting here, who's organizing much of the conference, so thank you very much for that. And it's going to be a conference like focused on like it's going to be for developers and like DevOps people, like the more professional admins, I think, because we want to keep it relatively small. So yeah, it's going to take place in the beginning of November in Berlin. You're all invited.
I'm a little confused here. We have two books that have been taken. It's like one book voucher and one disc. Have we really only asked 4 questions?
Well, I only have 2 questions left. Right?
All right, well, let's take it. Let's go then.
So the next question is, how many questions have I asked so far?
Over here in the, I'm sorry. Yes, perfect. Take,
That is incorrect. I mean, okay, in a way it's correct. 7 is correct. Well, I mean, 4 is also correct, right? Like it's, we should check it. That was a stupid question in that way. And the last one, I think is the most important one. What's the name of the after party bar for tonight?
Check and shirt or White Oak Tavern. Bingo. All right, everybody, let's head over there. Quick word. What I'm given to understand about the hard drives that everyone has gotten from this is there are a couple of conditions. One is you can't return them for warranty. There is no warranty. You break it, you keep both parts. 2.